Hello, and welcome to a journey that will challenge everything you think you know about the stage upon which our lives unfold. If Stephen Hawking showed us the universe's origin, Brian Greene now guides us to inspect the very fabric of reality itself in his profound work, The Fabric of the Cosmos, Space, Time, and the Texture of Reality. We begin with the most familiar concept, yet the most misunderstood: space. For centuries, our intuition, reinforced by Isaac Newton, treated space as a silent, invisible backdrop, an empty, infinite void that existed independently of anything within it. Space was the absolute container, unchanging and unaffected by the events transpiring inside. It was simply the rigid stage upon which the cosmic drama played out. Time, similarly, was a uniform, universal clock, ticking the same rate for everyone, everywhere. This was the view of absolute space and absolute time. This intuitive model, however, is a profound illusion, a consequence of our limited human experience confined to slow speeds and weak gravitational fields. The revolution that shattered this view came with Albert Einstein. Einstein showed us that space is not an empty, passive void, but a physical, dynamic entity. It is not a container. It is an active participant in the universe. This physical entity is fused with time, creating the unified four-dimensional fabric known as space-time. Imagine dropping a bowling ball onto a trampoline. The trampoline sheet itself, the fabric of space, is deformed by the ball's mass. This deformation is not an external force, it is a change in the shape of the space itself. Einstein's general theory of relativity dictates that gravity is nothing more than this curvature. A planet orbits a star not because an invisible force is pulling it, but because the planet is following the straightest possible path, a geodesic on a space-time surface that has been warped by the star's immense mass. This conceptual shift transforms space from a geometric concept into a physical field, much like a magnetic field or an electric field. This field has tension, ripples, and elasticity. It can be stretched, compressed, and distorted. The immediate consequence of this understanding is that space is relative. As we learned from the failure of the Michelson-Morley experiment to find the luminiferous ether, there is no absolute rest frame in the universe. Your measurement of distance, of space, depends entirely on your motion. If you are moving relative to another observer, you will measure distances and lengths differently than they do. This physical nature of space leads to the prediction of gravitational waves. Just as dropping a stone in a pond creates ripples that travel across the surface, the violent motion of massive objects, such as two black holes colliding, creates ripples in the fabric of space-time that travel outward at the speed of light. These gravitational waves are not waves through space, they are waves of space. As they pass, they momentarily stretch and compress the distances between objects. The successful detection of these minute ripples by experiments like LIGO in 2015 was the final direct confirmation that space is indeed a physical, active, and pliable medium, completing the transition from the intuitive Newtonian void to the dynamic physical stage of Einstein. Having established the physical reality of space, we must now turn our attention to its inseparable partner, time. Like space, time was long conceived of as an absolute, universally consistent quantity, ticking away at the same rate for all observers. This intuitive notion of a universal now is deeply embedded in our language and our philosophy. Albert Einstein's special theory of relativity, unveiled in 1905, forever destroyed this concept of a universal now. The theory is built on two simple yet revolutionary postulates. The laws of physics are the same for all non-accelerating observers, and the speed of light is the same for all observers, regardless of their own motion. The consequence of this constancy of light speed is the relativity of simultaneity. Events that happen simultaneously for one observer will not be simultaneous for an observer moving relative to the first. Imagine two observers, one standing still on a platform and one moving rapidly past in a train. If two lightning bolts strike the ends of the platform, the observer standing still might measure them as simultaneous. However, the observer on the train, moving towards one strike and away from the other, will measure the strike they move towards as happening first. Both observers are correct within their own frame of reference. There is no universal arbiter, no cosmic clock to declare which event truly happened first. Simultaneity is relative. This blurring of now means that the universe cannot be divided into a universal past, a universal future, and a universal present. Instead, space and time must be viewed as a single unified entity, space-time. In this four-dimensional space-time continuum, every event we experience, from the first moment of the Big Bang to the present moment, is just a point, defined by 3 spatial coordinates and 1 temporal coordinate. Our perception of time as a constantly flowing sequence of nows is merely how we traverse this fixed 4-dimensional reality. Furthermore, the rate at which time passes is not constant. It is affected by 2 cosmic factors, velocity and gravity. First, time dilation due to velocity. For an observer moving relative to another, time slows down for the moving observer. If a spacecraft travels near the speed of light, time on board the ship will tick slower relative to clocks on Earth. This is famously illustrated by the twin paradox. The twin who travels rapidly through space returns to find their sibling on Earth has aged more. This is not science fiction, it is a measurable, verifiable fact, constantly accounted for by systems like GPS satellites. Second, time dilation. Due to gravity, as dictated by general relativity, time runs slower in stronger gravitational fields. The deeper you are in a gravitational well, closer to a massive object, the slower your clock will tick compared to a clock in a weaker field. This means time moves slightly slower for you on the ground than it does for someone living on a mountaintop. This effect is also verified daily, as GPS satellites, which operate high in a weaker gravitational field, have their clocks adjusted to account for the fact that time moves faster for them than it does on Earth's surface. Thus, time is not an absolute river flowing uniformly for everyone. It is a relative, flexible component of the space-time fabric, with its flow rate dependent on your location and your speed. The intuitive sense of a universal present is merely an illusion created by the fact that the vast majority of our motion and our gravitational environment are essentially identical. Our journey into the core of reality leads us back to the most pervasive yet weakest of all forces, gravity. As we established, Albert Einstein's general theory of relativity, published in 1915, entirely redefined this fundamental force, transforming it from a mysterious pull across vast distances into an inherent property of space-time itself. Einstein postulated that the universe is woven from a single, unified, 4-dimensional fabric. The presence of mass and energy causes this fabric to curve, warp, and distort. This curvature is what we perceive as gravity. Imagine space-time as a perfectly smooth level sheet. If you roll a marble across it, it travels in a straight line. Now, place a heavy object, a star for instance, on the sheet. The object creates a dent or a curvature. If you roll the marble near this dent, its path is deflected inward, making it orbit the heavy object. The marble is not being pulled by an invisible rope, it is simply following the straightest possible path, a geodesic in the now curved surface. This geometrical interpretation is the essence of general relativity. Planets orbit the Sun not because of an instantaneous force, but because they are trapped in the geometric warpage of space-time caused by the Sun's enormous mass. This theory implies that space-time is not merely a passive receptacle. It is a dynamic, physical medium that interacts directly with matter. This dynamic property is essential for the structure of the cosmos, dictating everything from the orbit of the planet Mercury, whose elliptical path is slightly corrected by Einstein's theory compared to Newton's, to the ultimate fate of massive stars. The theory also revealed that even light is subject to gravity. Since light travels along the curves of space-time, its path is bent as it passes near massive objects. This was famously proven during the solar eclipse of 1919, where observers saw starlight passing near the Sun deflected exactly as predicted by general relativity. The most violent consequence of this warped geometry is the formation of a black hole. When a star exhausts its fuel and its mass is too great for any internal pressure to resist, it collapses endlessly under its own gravity. The space-time around it is warped so severely that the star punches a hole in the fabric of reality. This hole contains a singularity, a point of infinite density, and is surrounded by the event horizon, the boundary from which nothing, not even light, can ever escape. The detection of these geometrical distortions is now possible. The violent motion of massive objects, such as colliding black holes, generates ripples in the fabric of spacetime itself. These gravitational waves, predicted by Einstein, are not waves travelling through space, but waves of space. And their successful detection by the LIGO experiment confirmed that the geometry of the universe is a fluid, active participant in cosmic events. Having explored the massive classical reality of spacetime governed by general relativity, we must now turn to the microscopic probabilistic reality governed by quantum mechanics. The grand, unfinished project of physics is to bridge the divide between these two realms, the very large and the very small, in a unified theory. Quantum mechanics reveals that at the microscopic level, the realm of atoms and subatomic particles, energy, momentum, and other quantities do not exist in a smooth continuous flow, but in discrete packets called quanta. This realization, initiated by Max Planck in 1900, introduced fundamental randomness to the universe, breaking the iron grip of classical determinism. One of the cornerstones of this microscopic reality is Werner Heisenberg's uncertainty principle. This principle states that we cannot know with perfect accuracy both the position and the velocity of a particle simultaneously. This is not due to clumsy instruments. It is an inherent, inescapable property of nature itself. At the quantum level, particles exist in a probabilistic state, meaning only the likelihood of their behavior can be calculated. This probabilistic reality stands in stark contrast to general relativity's smooth deterministic geometry. The conflict between the two theories becomes acute under extreme conditions. At the singularity, general relativity predicts a point of infinite density inside a black hole or at the moment of the Big Bang. At this point, distances are so small and gravity is so strong that the chaotic, probabilistic effects of quantum mechanics cannot be ignored. The smooth geometry of relativity breaks down completely. In the vacuum. According to quantum mechanics, empty space is not empty. It is a roiling, seething foam of virtual particles constantly popping into and out of existence. This activity imparts a calculated, though enormous, amount of energy to the vacuum. When physicists try to mathematically merge the two theories, this quantum activity causes catastrophic results. The immense energy of the virtual particles, when fed into Einstein's equations, predicts an infinite curvature of spacetime, which is mathematically absurd and contradicts the relatively smooth universe we observe. This mathematical breakdown confirms that both general relativity and quantum mechanics are incomplete partial theories. The universe operates under a single set of rules, and the fact that these two theories conflict proves that there must be a deeper, more fundamental theory, the quantum theory of gravity, or the theory of everything that resolves their contradictions. The current leading theoretical attempts to bridge this divide, such as string theory and M-theory, suggest that the universe is far more complex than 4 dimensions, and is built upon vibrating fundamental units rather than point particles. The entire intellectual energy of modern physics is focused on unlocking this single set of rules that governs both the gentle curve of a planet's orbit and the violent, uncertain dance of subatomic particles. The central drama in modern physics revolves around the inability to reconcile the two greatest achievements of the 20th century, general relativity and quantum mechanics. The philosophical necessity of finding a single unified theory is obvious, as the universe surely operates under one consistent set of rules. The failure to unify them points to a deep misunderstanding of nature at its most fundamental level. The physical conflict between the two theories is not abstract, it is intensely mathematical and known as the infinity problem. General relativity describes gravity as the smooth, gentle curvature of space-time, a classical view that works perfectly on the scale of planets and galaxies. Quantum mechanics, however, introduces chaos and uncertainty at the smallest scales, describing energy and momentum as existing in discrete, unpredictable packets. When physicists attempt to merge the two, to create a quantum theory of gravity, they try to account for the gravitational effects of quantum phenomena. The first source of the infinity problem lies in the quantum vacuum. According to quantum field theory, empty space is anything but empty. It is a constantly roiling, seething foam where virtual particles, particle and antiparticle pairs, spontaneously pop into existence and annihilate each other in the blink of an eye. Although these particles are fleeting, they possess enormous quantifiable energy. When this immense energy from the virtual particles is mathematically plugged into the equations of general relativity, the result is a catastrophe. Relativity dictates that energy curves spacetime, and the vast calculated energy of the quantum foam should create an infinite amount of gravitational pull. Mathematically, this predicts that the universe should have infinite curvature, meaning it should have instantaneously collapsed into an infinitely dense point. This result is physically absurd. We observe a universe that is relatively smooth, expanding, and governed by finite gravity. The infinity problem confirms that the current mathematical framework for uniting the two theories is fundamentally flawed. It demonstrates that the two theories, as currently formulated, are not meant to meet. They are merely partial descriptions that break down when they attempt to describe the same extreme conditions, such as the initial moment of the Big Bang or the interior of a black hole. The ongoing search for a theory of everything is, therefore, a search for a new mathematical language, a language like string theory, that can describe the smooth flow of spacetime and the chaotic dance of quantum particles without generating this catastrophic non-physical result. The true unified theory must naturally cancel out these mathematical infinities, revealing the finite, elegant structure of reality underneath. The most promising, though most abstract candidate for resolving the infinity problem and achieving a quantum theory of gravity is string theory. This theory proposes a radical and beautiful philosophical shift in our view of fundamental reality. For centuries, the building blocks of matter, from the atoms of the ancient Greeks to the quarks and electrons of modern particle accelerators, have been treated as zero-dimensional, point-like particles. According to this point-particle view, when two particles interact, they collide at a single point in space-time, which is precisely where the mathematical infinities arise in the quantum gravity calculations. String theory eliminates this problem by replacing the point-like particles with tiny, one-dimensional, vibrating filaments called strings. These strings are incredibly small, far too small to ever be observed directly by current technology. The profound beauty of this idea is that every fundamental particle and force is merely a different vibrational mode of a single type of string. Imagine a violin string. Depending on how it vibrates, it can produce a wide range of musical notes. Similarly, in string theory, the different vibrational frequencies of the fundamental string correspond to the different particles we observe. One vibration pattern might be an electron, another a quark, and yet another, crucially, the graviton, the hypothetical particle that carries the gravitational force. This simple conceptual change, from points to loops of string, resolves the infinity problem. When two strings interact, they no longer collide at a single problematic point. Instead, their interaction is smeared out over a small finite area as they momentarily merge and separate. This spreading out of the interaction smooths the quantum fluctuations and mathematically cancels out the catastrophic infinities that ruined previous attempts to merge gravity and quantum mechanics. String theory, therefore, inherently includes gravity as part of its framework, making it the most mathematically viable candidate for a theory of everything. However, string theory comes with a profound counterintuitive cost. For its equations to be mathematically consistent, they require space-time to have 10 or 26 dimensions, vastly exceeding the 4, 3 spatial and 1 temporal we directly experience. The theory proposes that the extra dimensions are compactified, curled up into spaces so incredibly tiny that they are beyond our ability to detect them. The final unified theory must explain not only how the strings vibrate, but also the precise geometric structure of these hidden dimensions, as their shape dictates the physical laws we observe in our familiar 4 dimensions. The realization that string theory requires 10 or 26 dimensions for mathematical consistency forces us to confront a profound question about the physical architecture of reality. If these extra dimensions truly exist, why can we only perceive 3 dimensions of space, up, down, left, right, forward, backward, and 1 dimension of time? The explanation lies in the concept of compactification. String theory proposes that while the 3 large spatial dimensions we experience are vast and extended, the additional dimensions are curled up or compactified into spaces of incredibly small size. They are so tiny that they are beyond the resolving power of any current instrument, which is why they remain hidden from our direct perception. Imagine a garden hose stretched across a lawn. From a distance, it appears to be a one-dimensional line. An ant crawling along the hose, however, perceives a second dimension. It can move around the circumference of the hose. This circumference is the compactified dimension. For us, observing from afar, this dimension is invisible. Similarly, the extra dimensions in string theory are believed to be curled up into incredibly complex six-dimensional shapes at every single point in our familiar three-dimensional space. The size of these curled-up dimensions is thought to be near the Planck length, which is unimaginably small. The shape and geometry of these compactified dimensions are of crucial importance to the entire structure of the universe. In string theory, the way the fundamental strings vibrate is dictated by the geometry of the space they inhabit. This means that the precise shape of these hidden extra dimensions determines the physical constants and laws that we observe in our familiar four dimensions. For example, the mass of an electron, the strength of the electromagnetic force, or even the number of fundamental particles we observe, all these properties are thought to be geometric consequences of the curled-up structure. This introduces an extraordinary level of complexity to the search for the theory of everything. It is not enough to find the fundamental equations of the vibrating strings. Physicists must also determine which specific complex geometrical shape, out of potentially billions of possibilities, describes the true hidden architecture of our universe. The search for the correct geometry is a search for the cosmic DNA, the intricate blueprint that sets the rules for all of reality. This hidden, multi-dimensional architecture fundamentally reshapes our view of space, transforming it from a simple passive stage into a complex, curled-up geometric web that actively dictates the forces of nature. The complexity introduced by the extra dimensions of string theory led to a new philosophical frontier, the contemplation of the multiverse. As we discussed, the specific physical laws of our universe are determined by the precise shape of the hidden, curled-up dimensions. Unfortunately, the equations of string theory currently allow for a vast, perhaps infinite, number of possible shapes for these extra dimensions. Each shape corresponds to a different set of physical laws, different particle masses, and different force strengths. This enormous set of solutions is sometimes referred to as the cosmic landscape. Each valley and peak in this landscape represents a different stable vacuum state, or a different possible universe, each with its own unique laws of physics. If the laws of physics are set by the geometry of the extra dimensions, and if there are billions upon billions of stable geometries allowed by string theory, then it is plausible that our universe is just one of an infinite number of universes that exist in parallel or sequentially. This contemplation of the multiverse challenges the very idea of a single unique physical reality. The multiverse idea provides a powerful, though controversial, new perspective on the problem of fine-tuning, the observation that our universe's constants are perfectly set to allow for life. Instead of demanding a single, highly improbable reason why our universe is perfectly balanced, the multiverse suggests a statistical explanation. If there are an infinite number of universes, every possible set of physical laws is realized somewhere. We simply live in one of the universes where the forces happen to be suitable for the formation of stars, carbon, and intelligent life, because we could not possibly exist in a universe where the laws were chaotic or unsuitable. This view, rooted in the anthropic principle, avoids seeking a miraculous explanation for our existence by suggesting that the observer's presence dictates the environment they perceive. However, the multiverse concept faces severe philosophical and scientific hurdles. The primary difficulty is that these parallel universes, defined by different physical laws, are likely inaccessible to us. If we can never observe or interact with them, the multiverse remains a metaphysical hypothesis rather than a testable scientific theory. Despite the challenges, the multiverse idea, emerging directly from the mathematics of string theory, fundamentally alters our place in the cosmos. It suggests that the history and rules of our existence are not unique, but are merely one realization within an infinitely vast cosmic landscape of possibilities. The search for the ultimate theory thus becomes a search for the reason why our specific universe, with our specific laws, was selected or realized from this infinite array of possibilities. We must now consider the consequences of uniting general relativity and quantum mechanics at the smallest imaginable scales. We established that the failure to merge these theories lies in the infinity problem, where the calculated energy of the quantum vacuum causes space-time to collapse mathematically. But what does quantum mechanics suggest about space-time itself at these extreme sizes? As we approach the scale known as the Planck length, an unimaginably small distance that defines the size where quantum effects dominate gravity, the smooth, gentle geometry of space-time, as described by Einstein, must necessarily break down. At this minute scale, the uncertainty principle takes over. Just as the position and velocity of a particle become fundamentally uncertain, so too must the geometry and topology of space-time itself become uncertain. Space-time is no longer a smooth, predictable fabric. Instead, it becomes a chaotic, constantly fluctuating mess known as quantum foam. Imagine looking at the surface of a pond. From a distance, it appears flat and smooth. As you zoom in closer, you see small ripples. Zoom in further still, and you see the chaotic bubbling and surging of individual water molecules. Similarly, as we zoom into the fabric of space-time at the Planck scale, the fabric itself is not flat, it is boiling with extreme curvature and energy fluctuations. This quantum foam is a consequence of the intense momentary violations of energy conservation allowed by the uncertainty principle. Tiny amounts of energy can spontaneously appear and disappear, causing the geometry of space to fluctuate wildly. New dimensions might momentarily appear and vanish, and miniature wormholes, tunnels connecting disparate parts of space, might flicker into and out of existence. The transition from the smooth space-time we experience to the turbulent quantum foam is where the laws of general relativity cease to be applicable. The very concepts of distance and time lose their definite meaning in this chaotic environment. String theory offers a conceptual way to navigate this quantum foam. Recall that the fundamental strings are themselves incredibly tiny. Their size is approximately the Planck length. Because the strings are the fundamental building blocks, they cannot probe distances smaller than their own size. The strings effectively smooth out the raging turbulence of the quantum foam. According to string theory, the chaotic geometry below the Planck length is replaced by the orderly, if multi-dimensional, geometry of vibrating strings. The idea of quantum foam forces us to realize that our perception of the universe's continuity is an illusion born of scale. Reality, when examined at its absolute foundation, is a shimmering, probabilistic, and radically uncertain environment where the very nature of existence is momentarily being renegotiated at every point. The philosophical goal of the theory of everything is not just to describe matter, but to explain the origin and strength of the fundamental forces that govern the cosmos: gravity, electromagnetism, and the strong and weak nuclear forces. String theory provides an elegant, unified explanation by suggesting that all forces are simply geometric consequences of the multidimensional structure of space-time. Recall that string theory requires 10 or 26 dimensions for its mathematical consistency. The way these extra dimensions are compactified, curled up into tiny, intricate shapes, is what determines the physical laws we observe in our familiar 4 dimensions. The key insight is that forces and particles are related to vibrations in these dimensions. The graviton, the particle that transmits gravity, is simply one specific vibration pattern of the string. But what about the other forces? The other forces, such as electromagnetism, are mathematically linked to the shape and structure of the extra curled-up dimensions. If the extra dimensions were to somehow expand or change their shape, the strength of the electromagnetic force, or the mass of the electron, would also change. The forces are not arbitrary. They are the geometric echoes of the hidden architecture of space. Imagine the extra dimensions as a complex, microscopic structure attached to every point in our visible space. The interactions we perceive as forces are really just the ways in which particles, represented by vibrating strings, move through or interact with the intricate geometry of this hidden structure. This unification is far more profound than the previous, separate descriptions of forces. It suggests that all of physics, once divided into separate fields like gravity, particle physics, and meant electromagnetism, is rooted in a single, common origin: geometry. The physical universe is a universe of geometric possibilities. The implications for the search for the theory of everything are immense. If the theory is found, it will not be enough to write down the equations of the vibrating strings. The theory will be complete only when the precise geometric structure of the curled-up dimensions, the exact, intricate shape that dictates all the constants, is identified. This realization fundamentally changes the nature of the inquiry. The search for a unified theory becomes a search for the right geometry, the specific architecture of the universe that results in the physical laws we measure in our laboratories and observe in the cosmos. The complexity of this geometrical problem, with potentially billions of possible shapes, underscores the monumental challenge that remains in completing the final theory. Having explored the geometrical reality of space, we must now delve deeper into the enigma of time. Our fundamental intuitive experience is that time flows relentlessly forward, carrying us from the known past toward the unknown future. The crucial philosophical question is, why can't we go back? Why does time possess this strict unidirectionality? In the fundamental laws of physics, the equations of Newtonian mechanics, electromagnetism, and even general relativity, there is no distinction between the past and the future. If you could film a simple physical event such as two billiard balls colliding, and then run the film backward, the reversed action would perfectly obey the same laws of motion. The equations are time-symmetric, yet in the macroscopic world we inhabit, time is definitively one way. This directionality is defined by the thermodynamic arrow of time, which is dictated by the second law of thermodynamics. This law states that the total entropy, or disorder, of the universe must always increase. Events that increase disorder are easy and frequent. A glass breaks, a house decays, or milk mixes with coffee. Events that decrease disorder are impossible in our experience. A broken glass never spontaneously reassembles itself, and smoke never flows back into a cigarette. The second law of thermodynamics is the physical mechanism that separates the past from the future. The past is characterized by lower entropy, more order, and the future is characterized by higher entropy, more disorder. The profound mystery then shifts. If the underlying laws of physics are time-symmetric, why did the universe begin in a state of extraordinarily low entropy, a state of extreme order? If the universe had started in a highly disordered state, its entropy could not have increased significantly, and we would not perceive a strong thermodynamic arrow of time. The existence of a strong arrow of time, which allows for complex, ordered structures like stars, planets, and consciousness to form, depends entirely on the highly ordered initial state of the Big Bang. Some theories attempt to resolve this by suggesting the universe is cyclical, perhaps bouncing between a Big Bang and a big crunch. However, if entropy increases with every cycle, the universe would get larger and longer with each iteration, meaning the cycles are not truly identical. The most profound realization is that our sense of time's direction is tied to this fundamental cosmic tendency toward increasing disorder. We are simply riding the wave of increasing entropy from the ordered beginning to the chaotic end. The physical arrow of time established by the relentless increase of entropy dictates the other arrow that governs our consciousness, the psychological arrow of time. This arrow defines the direction in which we can remember the past but not the future. Our perception of time as a linear flow is inextricably linked to our ability to form and store memories. Memories are not abstract concepts. They are physical records encoded in the ordered structure of our brains or in the physical states of a computer's hardware. The process of recording any memory, whether the information is stored in a neuron or on a hard drive, is a physical process that requires energy. When energy is used, it generates heat and causes the dissipation of that energy, which increases the total disorder or entropy of the surrounding environment. To form a memory is to create an island of order, the stored information, in a sea of increasing disorder, the waste heat. The physical laws are structured such that the creation of a memory is always accompanied by an increase in the universe's total entropy. This physical reality means that we can only process information and form memories in the direction of time in which entropy is increasing. The past is simply the direction of time where the total entropy was lower, and the future is the direction where it is higher. If the second law of thermodynamics were reversed, if the universe began contracting and entropy was somehow decreasing, our ability to form memories would also necessarily reverse. We would then remember the future and be unable to recall the past. However, we have established that even if the universe were to contract, the chaotic nature of that event would still likely cause entropy to increase, protecting the direction of our memory. The realization that our consciousness and our perception of time are governed by this vast cosmic principle of increasing disorder is humbling. Our sense of self, our history, and our perception of linearity are all consequences of the universe's initial highly ordered state and its inexorable march toward maximum entropy. Our personal internal experience of time flow is therefore not merely a neurological quirk. It is a fundamental echo of the universe's deepest thermodynamic tendency. We are creatures of the thermodynamic arrow. Having explored the geometrical reality of space, we must now delve deeper into the enigma of time. Our fundamental intuitive experience is that time flows relentlessly forward, carrying us from the known past toward the unknown future. The crucial philosophical question is, why can't we go back? Why does time possess this strict unidirectionality? In the fundamental laws of physics, the equations of Newtonian mechanics, electromagnetism, and even general relativity, there is no distinction between the past and the future. If you could film a simple physical event such as two billiard balls colliding and then run the film backward, the reversed action would perfectly obey the same laws of motion. The equations are time-symmetric. Yet in the macroscopic world we inhabit, time is definitively one way. This directionality is defined by the thermodynamic arrow of time, which is dictated by the second law of thermodynamics. This law states that the total entropy or disorder of the universe must always increase. Events that increase disorder are easy and frequent. A glass breaks, a house decays, or milk mixes with coffee. Events that decrease disorder are impossible in our experience. A broken glass never spontaneously reassembles itself. The second law of thermodynamics is the physical mechanism that separates the past from the future. The past is characterized by lower entropy, more order, and the future is characterized by higher entropy, more disorder. The profound mystery then shifts. If the underlying laws of physics are time-symmetric, why did the universe begin in a state of extraordinarily low entropy, a state of extreme order? If the universe had started in a highly disordered state, its entropy could not have increased significantly, and we would not perceive a strong thermodynamic arrow of time. The existence of a strong arrow of time, which allows for complex, ordered structures like stars, planets, and consciousness to form, depends entirely on the highly ordered initial state of the Big Bang. Some theories attempt to resolve this by suggesting the universe is cyclical, perhaps bouncing between a Big Bang and a Big Crunch. However, if entropy increases with every cycle, the universe would get larger and longer with each iteration, meaning the cycles are not truly identical. The most profound realization is that our sense of time's direction is tied to this fundamental cosmic tendency toward increasing disorder. We are simply riding the wave of increasing entropy from the ordered beginning to the chaotic end. The physical arrow of time established by the relentless increase of entropy dictates the other arrow that governs our consciousness, the psychological arrow of time. This arrow defines the direction in which we can remember the past but not the future. Our perception of time as a linear flow is inextricably linked to our ability to form and store memories. Memories are not abstract concepts. They are physical records encoded in the ordered structure of our brains or in the physical states of a computer's hardware. The process of recording any memory, whether the information is stored in a neuron or on a hard drive, is a physical process that requires energy. When energy is used, it generates heat and causes the dissipation of that energy, which increases the total disorder or entropy of the surrounding environment. To form a memory is to create an island of order, the stored information, in a sea of increasing disorder, the waste heat. The physical laws are structured such that the creation of memory is always accompanied by an increase in the universe's total entropy. This physical reality means that we can only process information and form memories in the direction of time in which entropy is increasing. The past is simply the direction of time where the total entropy was lower, and the future is the direction where it is higher. If the second law of thermodynamics were reversed, if the universe began contracting and entropy was somehow decreasing, our ability to form memories would also necessarily reverse. We would then remember the future and be unable to recall the past. However, we have established that even if the universe were to contract, the chaotic nature of that event would still likely cause entropy to increase, protecting the direction of our memory. The realization that our consciousness and our perception of time are governed by the vast cosmic principle of increasing disorder is humbling. Our sense of self, our history, and our perception of linearity are all consequences of the universe's initial highly ordered state and its inexorable march toward maximum entropy. Our personal internal experience of time flow is therefore not merely a neurological quirk. It is a fundamental echo of the universe's deepest thermodynamic tendency. We are creatures of the thermodynamic arrow. We have established the thermodynamic arrow of time dictated by increasing disorder and the psychological arrow determined by the physical act of forming memories. But there is a third grand cosmic arrow that aligns with these two, the cosmological arrow of time. This arrow points in the direction that the universe is expanding rather than contracting. For the three arrows of time, thermodynamic, psychological, and cosmological, to all point in the same direction, there must be a fundamental connection between the universe's initial state, its expansion, and the creation of order. The cosmological arrow is tied directly to the fate of the universe. If the universe's average density were high enough, gravity would eventually halt the expansion, and the universe would begin to contract toward a big crunch. The crucial question is whether the arrow of time would reverse during this contraction phase. Brian Greene explores the profound, albeit controversial idea that if the universe were to contract, time itself might reverse. If the universe were perfectly time-symmetric, the Big Crunch would be the time reverse of the Big Bang, a phase of decreasing entropy where disorder would spontaneously diminish. In such a scenario, the thermodynamic arrow would flip, and memories would begin to form in the direction of decreasing entropy, meaning we would start to remember the future. However, most modern cosmological thought suggests this reversal is unlikely. Even if the universe were to contract, the physical forces and interactions involved in the gravitational collapse are so violent that they would likely continue to increase the total disorder entropy of the system. The chaotic environment of a collapsing universe would accelerate the mixing and randomization of particles. The profound philosophical implication is that the very existence of intelligent life depends on the alignment of these arrows. Intelligent life requires the creation of complex, ordered structures, low entropy, in a process that is irreversible. Strong time arrow. If the universe were ever to contract, the conditions would quickly become too hot and chaotic for complex life to survive. The cosmological arrow, therefore, explains a subtle form of the anthropic principle. We observe the universe to be expanding because only in the expanding phase, when entropy is safely increasing, are the conditions right for us to exist and observe the flow of time. We are creatures of the expansion. The most captivating challenge to the unidirectional flow of time is the possibility of time travel, particularly into the past. While the thermodynamic arrow suggests this is physically impossible, as it would involve creating order from chaos, the equations of general relativity contain theoretical solutions that allow for time loops, challenging the fundamental linearity of existence. One such path to the past involves wormholes, theoretical tunnels in the fabric of space-time connecting two distant points or two different moments in time. If a wormhole could be created and its entrances manipulated in specific ways, it could become a time machine. The primary obstacle to such time travel is the inevitable paradox that arises, most famously the grandfather paradox. If you travel into the past and prevent your own existence, fundamental causality is violated. Physicists believe that nature possesses a powerful defense mechanism against such causal violations, a concept known as chronology protection. This principle, most famously articulated by Stephen Hawking, suggests that the laws of physics conspire to prevent the formation of time loops. One way chronology protection might manifest is through quantum fluctuations. If an attempt were made to create a time machine, perhaps by trying to stabilize a wormhole, the energy required to do so would trigger a catastrophic feedback loop involving virtual particles. The intense gravitational effects of these particles at the throat of the wormhole would increase the energy density of space-time so violently that the region would instantaneously collapse, preventing the time loop from ever fully forming. This means that the laws of physics, at their deepest quantum level, may inherently favor causality over contradiction. The universe appears to have a built-in mechanism to protect history. Hawking famously offered a simple, practical argument against the possibility of macroscopic time travel to the past. If time travel were possible, we would be overrun by tourists from the future. The conspicuous absence of such visitors suggests that despite the theoretical loopholes in general relativity, the quantum laws of the universe are too strict to allow the creation of a working time machine. The question of time travel, therefore, is not just a technological one. It is a profound philosophical inquiry into the nature of causality. The universe seems to operate under a principle of self-consistency, where the very fabric of space-time guards its own history against the illogical nightmare of paradox. The special theory of relativity forces us to abandon the deep-seated intuition that there is a universal moment called now, a single objective present shared by everyone in the cosmos. This realization has a profound, almost disturbing philosophical consequence. If there is no universal now, then the past and the future are just as real and fixed as the present. Recall the core finding of relativity. Simultaneity is relative. Events that occur at the same time for one observer will occur at different times for an observer in relative motion. Imagine an event that we consider to be in our future. Say, the collision of two distant stars 1,000 years from now. For an observer moving at a high enough velocity relative to us, that collision already lies in their present moment, or even their past. Since both observers are equally correct according to the laws of physics, this suggests that all moments in time, past, present, and future, are equally real and fixed in the vast four-dimensional structure of space-time. This is the philosophical view of eternalism, often called the block universe theory. In this model, space-time is a static, unchanging block, and all moments in time, like points on a line, simply exist. Our human perception of time as a flow, the feeling that we are constantly moving from one moment to the next, is merely the way our consciousness experiences this fixed reality. The feeling of flow, or becoming, is not a property of the external universe, but a psychological feature of our minds, perhaps tied to the psychological arrow of time. This perspective challenges the idea of time as an active, flowing entity and replaces it with the concept of time as a dimension, much like space. We do not feel like we are flowing through the north-south dimension of space, we simply experience our movement within it. Similarly, our experience of time is merely our movement through the time dimension of the block universe. The block universe view also deeply impacts the concept of free will. If the past, present, and future all equally exist, then all our future decisions are already fixed points in this space-time block. The agonizing choice you feel you're making right now is, in fact, an event that has always existed at that specific coordinate in the block universe. While the uncertainty principle of quantum mechanics suggests a fundamental randomness at the smallest scales, which might appear to create a fuzziness or uncertainty in the block, relativity itself strongly implies that the future is just as fixed and real as the past. The true nature of time, therefore, forces us to question the deepest intuitions of our existence, that the future is open, and that the moment we call now is universally shared. The classical theory of gravity, general relativity, breaks down completely when describing reality at the most minute scales, leading us into the realm of quantum mechanics, and the fundamental uncertainty it introduces to the fabric of space-time. As we established, the problem of unification arises because the smooth, continuous geometry of general relativity conflicts with the chaotic, discrete nature of the quantum world. This conflict becomes dominant at the Planck scale, an unimaginably small size that defines the domain where quantum effects rule gravity. At this minute scale, the uncertainty principle dictates that the geometry of space-time itself cannot be precisely fixed. The fabric of space is not smooth, but is subject to violent random fluctuations in energy and curvature. This turbulent environment is known as quantum foam. Imagine the surface of space-time as a perfect sheet. At the Planck scale, this sheet is not flat, but is boiling and bubbling with extreme intensity. Miniature wormholes, tunnels connecting one part of space-time to another, are thought to constantly flicker into and out of existence, and the topology of space, its fundamental shape, is constantly changing. In this region of quantum foam, the classical concepts of distance and time lose their definite meaning. The very structure of space-time is fuzzy and probabilistic. The implications of the quantum foam are critical for understanding the forces of nature. The quantum foam generates enormous energy from the constant creation and annihilation of virtual particles. If this energy were to be fully accounted for by general relativity, it would collapse the universe instantly. This is the infinity problem in its most physically acute form. String theory provides the leading theoretical defense against the quantum foam's destructive power. Because the fundamental strings are themselves the size of the Planck length, they cannot probe distances smaller than their own size. The strings effectively smooth out the chaos, replacing the turbulent geometry with the orderly, multidimensional geometry defined by their vibrations. String theory suggests that the quantum foam is tamed by the strings, revealing a deeper, simpler reality built upon one-dimensional filaments rather than zero-dimensional points. The failure of our current theories is simply the failure to use the correct language, the language of strings and their multidimensional geometry, to describe the physics at the fundamental level where space and time cease to be smooth and continuous, and instead become discrete and probabilistic. The journey to understand the expanding universe was not a straightforward path of discovery, but one marked by profound resistance to the dynamic nature of gravity. After Newton established his law of universal gravitation in 1687, it was clear that an infinite static universe was inherently unstable. Gravity, being an attractive force, would inevitably cause a collection of stars to collapse inward toward a single point. Yet the belief that the universe was static, unchanging and existing eternally in its current state, was so deeply ingrained that even the greatest minds sought to defy the logical conclusion of their own theories. Prior to the 20th century, the idea that the universe could expand or contract was simply not contemplated. Instead of accepting the inevitable collapse predicted by their own laws, scientists attempted to modify gravity itself. They suggested that at very long distances, gravity might become repulsive, pushing stars apart rather than pulling them together, thereby maintaining a perfect balance. However, this balance model would have been unstable. If some stars moved even slightly closer to each other, the attractive force would dominate, and they would collapse inward. If they moved slightly farther apart, the repulsive force would win, and they would rush away from each other. The universe would either rapidly collapse or fly apart. This resistance to the dynamic universe reached its peak with Albert Einstein. When Einstein formulated the general theory of relativity in 1915, the theory itself naturally suggested a dynamic cosmos, one that must either be expanding or contracting. Yet Einstein, sharing the static bias of his time, initially found the idea of a moving universe disturbing. To reconcile his revolutionary theory with the prevailing belief in a static cosmos, Einstein performed an extraordinary yet ultimately flawed intellectual maneuver. He introduced a new mathematical term into his equations. This term was the cosmological constant. The cosmological constant was an artificial force designed to work in opposition to gravity. It was a repulsive energy inherent in the fabric of space-time itself, existing independently of any matter. It was precisely designed to exactly balance the attractive force of gravity, thus holding the universe in a state of perfect static equilibrium. The ultimate irony came in 1929, with the observational confirmation of cosmic expansion by Edwin Hubble. Hubble's discovery that galaxies are moving away from us proved that the universe was not static. The universe was expanding. Faced with this observational fact, Einstein was forced to abandon his cosmological constant. He later referred to the introduction of this constant, a mathematical term he inserted purely to preserve a preconceived notion about the universe's state, as his greatest mistake. The episode serves as a powerful testament to how deeply entrenched philosophical biases can, for a time, obscure even the most obvious scientific truths inherent in one's own equations. The universe, against centuries of human intuition, was revealed to be a dynamic, evolving entity. The dynamic nature of the universe leads us to the most extreme phenomena predicted by general relativity, the singularity. Whether at the Big Bang or the core of a black hole, the singularity represents a point of infinite density and curvature, where the very structure of space-time collapses and the laws of physics cease to apply. The unpredictability inherent in the singularity poses a profound challenge to science. To deal with the singularities that arise from stellar collapse, Roger Penrose proposed the cosmic censorship hypothesis. This conjecture states that the singularity formed from the collapse of a star is always hidden from outside observers by an event horizon. The singularity is always cloaked. It is never naked. The philosophical and scientific importance of this hypothesis is immense. If a singularity were to become naked, directly visible to the external universe, without the protective shield of an event horizon, its point of infinite density and unpredictable nature would cause the predictability of the entire universe to break down. Since the universe is observed to follow predictable laws, this hypothesis suggests that the laws of nature conspire to ensure that all singularities remain hidden. While mathematicians like Hawking and others have found theoretical solutions to Einstein's equations that do allow for naked singularities, these solutions are typically highly specialized and unstable. The slightest perturbation or disturbance would cause the naked singularity to quickly cloak itself again behind an event horizon. Thus, the consensus in physics remains that, in any realistic cosmic scenario, the singularity is always hidden. This cloaking mechanism is critical to the black hole's other great paradox, the information paradox. When matter, which carries a massive amount of information, falls across the event horizon and into the singularity, that information is seemingly lost forever to the outside universe. According to general relativity, the black hole is simplified to only its mass and spin. All the complex details of the material that formed it are wiped clean. However, this loss of information fundamentally conflicts with the principles of quantum mechanics, which insist that information must be preserved. If information is truly lost, it violates the time reversal symmetry inherent in quantum laws. The discovery of Hawking radiation only deepened the paradox. This radiation, produced by quantum effects near the event horizon, causes the black hole to slowly evaporate. If the black hole eventually disappears entirely, the original information must somehow be released. Yet Hawking radiation is purely thermal, it is random and carries no record of the specific information that fell in. The question is, if the black hole evaporates, where does the information go? This conflict, the inevitable collapse into a singularity versus the inviolability of information, highlights the limitations of our current partial theories. Neither general relativity nor quantum mechanics can fully describe this process. The black hole, therefore, serves as the ultimate theoretical laboratory, forcing physicists to search for the quantum theory of gravity that can finally resolve this fundamental paradox and provide a complete picture of the universe's dynamic evolution. The singularity theorems establish that according to general relativity, the universe must have begun with a Big Bang singularity. This point of infinite density is where the classical theory of gravity fails, signaling that the theory is incomplete. To go beyond this moment of failure, we must apply quantum mechanics to the universe's origin. The search for a quantum theory of gravity is essential to understanding the ultimate destiny of the universe. The early moments after the Big Bang can be described by known physics. The universe began in a state of extremely high temperature. As the universe expanded, its temperature dropped. When the size of the universe doubled, the temperature halved. At extremely high temperatures, collisions created particle-antiparticle pairs. About 1 second after the Big Bang, the temperature had dropped dramatically. At this stage, the universe was filled with fundamental particles. As the universe cooled further, some of these particles annihilated, leaving behind a small residual amount of matter. About 100 seconds after the Big Bang, the temperature had dropped enough for protons and neutrons to combine, forming hydrogen and helium nuclei. About 25% of the matter in the universe was converted into helium during this period. This prediction of primordial nuclear synthesis was made by George Gamow and Ralph Alpher in 1948. They also predicted that the remnants of these ancient reactions should still be detectable today as a cosmic radiation. The discovery of the cosmic microwave background in 1965 by Penzias and Wilson provided a major proof that the Big Bang model was correct. 1 million years after the Big Bang, the universe had cooled enough for electrons to combine with nuclei, forming atoms. Gravity began to slow the expansion in regions that were slightly denser than average. These denser regions collapsed to form galaxies and inside them, stars. Large stars burned quickly and ended their lives in supernova explosions, creating heavier elements like carbon, oxygen, and iron. Our Sun, a second or third generation star, formed about 5 billion years ago. However, despite its success, the Big Bang model left 4 large unresolved questions. The uniformity problem. Why is the universe so uniform? The temperature of the microwave background is almost identical in all directions. Light could not have travelled from one side of the early universe to the other to synchronize their temperatures. The flatness problem. Why is the expansion rate so perfect? The required precision for the initial expansion rate is astonishing. The smoothness problem. Where did the seeds for galaxies and stars come from? The early universe was almost perfectly smooth. The small density fluctuations needed to initiate gravitational collapse are not explained. The hotness problem. Why was the universe initially so hot? To answer these questions, we must incorporate quantum mechanics into the universe's origin. The enduring philosophical question is why the fundamental constants of nature are precisely tuned to allow for the existence of life. The precise values of these constants seem to be a series of lucky coincidences. If the laws of physics were slightly different, the universe would be drastically different, and life as we know it would be impossible. The observation that the universe is perfectly calibrated for the existence of intelligent life is captured in the anthropic principle. This principle offers 2 main interpretations to explain the fine-tuning. The The weak anthropic principle suggests that in a universe that is either very large or infinite, conditions suitable for life will necessarily arise in some regions. We, as conscious observers, are only able to exist and ask these questions because we happen to be in one of those regions. This interpretation argues that the laws might be random, but our observation is biased toward the regions where life is possible. The strong anthropic principle goes further, suggesting the existence of a multiverse, a vast number of separate universes, each with its own set of laws and physical constants. Only a small fraction of these universes would have laws that are suitable for the evolution of intelligent life. We exist in one of those special universes simply because we could not exist in any of the others. Hawking expressed philosophical unease with the strong anthropic principle. He found it difficult to accept that the entire universe, with its billions of galaxies, only exists for the sake of our limited ability to observe and think. Furthermore, science has historically rejected human-centered thinking. The anthropic principle, while thought-provoking, represents a potential defeat for science if it is used to explain away the fine-tuning as mere cosmic accident or luck. The hope remains that the final unified theory will prove that the constants of nature are not arbitrary at all, but are mathematically determined by the internal consistency of the theory itself. The scientific alternative to the anthropic principle is the inflationary theory, which provides a physical mechanism for solving the major problems of the Big Bang model. The failure of the standard Big Bang model to explain the uniformity and flatness of the universe, the problems that demanded an astonishing degree of fine-tuning in the initial state, pointed to a missing piece of physics. The universe appeared far too smooth and flat to have arisen from random initial conditions. This missing piece was provided by the inflationary theory, first proposed by Alan Guth in 1981. This theory suggests that the universe underwent an extremely short period of rapid, exponential expansion in the fraction of a second immediately following the Big Bang. During this period, the universe expanded at a rate far exceeding the speed of light. The mechanism driving this expansion involved the universe passing through a phase transition as it cooled. This transition released a tremendous amount of extra energy that acted as a repulsive anti-gravity force, causing space-time to inflate exponentially. The inflationary model provided elegant solutions to the core cosmological problems: the uniformity problem, horizon problem. Before inflation, the entire observable universe was a tiny region, small enough for light to travel across and synchronize its temperature. The exponential expansion then stretched this uniform, synchronized region across the vast distances we see today, explaining why the cosmic microwave background radiation is virtually the same temperature in all directions. The flatness problem. The enormous rapid expansion naturally drove the universe's geometry extremely close to the critical value needed to perfectly balance gravity and expansion. The universe was flattened by inflation, much like blowing up a tiny wrinkled balloon until its surface appears perfectly flat. The smoothness problem. The small density fluctuations needed to seed galaxies are explained by the inherent quantum uncertainties that were present in the tiny pre-inflationary region. Inflation stretched these microscopic quantum fluctuations into macroscopic density variations that eventually grew into galaxies and clusters of galaxies. Inflation also provided a neat answer to the question of where the universe's vast number of particles came from. Hawking explains that the universe's total energy is zero. The matter particles have positive energy, but their mutual gravitational attraction creates an equal amount of negative gravitational energy. These two components cancel out. Thus, the universe could spontaneously create all its matter and energy from nothing, without violating the conservation of energy. As has been famously said, the universe is the ultimate free lunch. The success of the inflationary theory showed that a wide range of messy, non-uniform initial conditions could be smoothed into the well-structured cosmos we observe. This moved the discussion away from relying on the philosophical notion of fine-tuning and toward a scientific mechanism. Even the inflationary theory, for all its success, still required a starting point, a field of energy to drive the initial expansion. This led Stephen Hawking and Jim Hartle to develop the no-boundary proposal, seeking to eliminate the need for any initial conditions, external forces, or boundary selections. This profound idea is rooted in the application of quantum mechanics to the entire universe, specifically through the mathematical concept of imaginary time. In imaginary time, time behaves like another dimension of space. This mathematical shift allows the universe to be modelled as a finite four-dimensional structure without any boundary or edge. Imagine the surface of the Earth. It is finite, but if you travel on it, you never encounter an edge. Similarly, the universe, when described using imaginary time, would start smoothly at a point, analogous to the North Pole, and expand without ever encountering a singular beginning or a boundary condition that needs to be arbitrarily set. Hawking's famous statement encapsulates this idea. The boundary condition of the universe is that it has no boundary. If this proposal is correct, it means the universe is a self-contained entity that simply is. It never began with a dramatic creation moment. The laws of quantum physics alone would dictate the universe's initial state, and it would be the one and only mathematically consistent state. The philosophical implication of the no-boundary proposal is immense. It suggests that the universe is logically and scientifically complete in and of itself. If the universe has no boundary or beginning, then the logical necessity for an external creator to set the initial clock or choose the starting conditions is removed. The debate then shifts from who created the universe to who created the laws of physics. Even if the universe is self-creating, the question remains, why are the laws of quantum gravity so perfect and rational that they permit the existence of complex structures like ourselves? The ultimate victory of human reason would be achieved when we find the complete unified theory that explains not only how the universe operates, but also why its existence and its laws are inevitable. This knowledge, the answer to why we exist, would be the final shared achievement of all humanity. We have traversed the vast landscape of the cosmos, from the static Earth-centered models to the dynamic, quantum-fluctuating reality of the expanding universe. In all these models, the concept of time has been central yet elusive. Newtonian physics gave us absolute time. Einstein's special relativity introduced relative time dependent on the observer's motion. And finally, quantum gravity introduced the strange spatial dimension of imaginary time. Yet, in our physical existence, time is undeniably linear and directional. In imaginary time, one can move forward and backward, much like moving in space. But in real time, the past and the future are fundamentally different. We possess memories of the past, but we have no knowledge of the future. Time seems to flow, and this flow is defined by the arrow of time. There are three distinct yet interconnected arrows that define this direction of time, and all three point in the same direction. The first is the thermodynamic arrow of time, the direction of time in which disorder or entropy increases. The second law of thermodynamics is the bedrock of this arrow. It states that the total entropy of a closed system must always increase. This law explains why we see events unfold in one direction, but never the reverse. A cup falls and shatters, increasing disorder, but the shattered pieces never spontaneously reassemble into a whole cup. The rising entropy implies the universe is moving from a state of high order to low order. The second is the psychological arrow of time, the direction in which we are able to remember the past but not the future. This arrow is fundamentally linked to the thermodynamic one. Memories are stored in our brains in an ordered state, but the process of recording a memory consumes energy, which leads to an increase in the total disorder, entropy, of the universe. We can only make memories in the direction of time in which entropy is increasing. The third is the cosmological arrow of time, the direction of time in which the universe is expanding rather than contracting. The crucial question is why these three arrows are aligned. Why did the universe begin in a highly ordered state? The no-boundary proposal derived from quantum gravity suggests that the universe began in a remarkably smooth and ordered state. The small quantum fluctuations present at the beginning provided the non-uniformity necessary to seed the formation of galaxies and stars. This ordered beginning naturally explains why the thermodynamic arrow and the cosmological expansion arrow point in the same direction. The distinction between the past and the future, enforced by the arrows of time, faces its ultimate theoretical test in the concept of time travel. While the psychological and thermodynamic arrows make travel into the past an improbable reversal of nature, the equations of general relativity provide tantalizing, albeit highly unstable, mathematical loopholes that might allow such a journey. The first theoretical spacetime model allowing travel into the past was found in 1949 by Kurt Gödel. Gödel's solution described a rotating universe where an astronaut could fly in a rocket ship and return to a point in time before they started their journey. Although observations show our universe is expanding, not rotating, Gödel's work established that time travel is theoretically compatible with the core framework of general relativity. Since then, other theoretical structures that create time loops have been identified, such as the space-time distortions near the interior of a black hole, or those potentially created by passing cosmic strings. While the twin paradox allows us to travel into the future by moving close to the speed of light, true travel into the past would require either surpassing the speed of light, which relativity forbids, or finding a shortcut through the cosmos. This shortcut is the wormhole, or Einstein-Rosen bridge. A wormhole is a tunnel-like structure that connects two distant regions of space-time, allowing travellers to cover vast distances in a short period. The major difficulty is that natural wormholes are highly unstable and would instantly collapse. To keep a wormhole open for travel, advanced civilizations would need to use matter with negative energy density. While this is forbidden by classical physics, quantum mechanics suggests it is possible on a small scale, a phenomenon confirmed by the Casimir effect. The possibility of travelling into the past through a wormhole inevitably leads to the logical nightmare of the grandfather paradox. If the past can be changed, fundamental contradictions arise. Two main theoretical resolutions exist for the paradox: the consistent histories approach. The past cannot be altered, and any attempt to change history is bound to fail. The alternative history hypothesis, multiverse theory. Travelling to the past causes a branching or split in history, creating a new alternative timeline. Hawking's philosophical answer to these paradoxes is the chronology protection conjecture. This conjecture posits that the laws of physics conspire to prevent macroscopic time travel. The attempt to create a time loop, perhaps by stabilizing a wormhole, would cause the quantum vacuum to generate intense energy fluctuations. This energy would cause the region to collapse, preventing the time loop from ever fully forming. Hawking offered a simple practical argument. If time travel to the past were physically possible, we would already be witnessing a constant influx of visitors from the future. The absence of such tourists suggests that the arrow of time we experience is a fundamental constraint of our physical reality. The journey through the cosmos reveals that the existence and fate of stars are governed by a delicate, profound balance between opposing forces. Every star's life cycle is a contest between the inward crushing force of gravity and the outward explosive pressure generated by nuclear fusion. A star begins its life as a cloud of gas, which gravity forces to contract and heat up until its core reaches the enormous temperatures required for hydrogen atoms to fuse and release energy. This energy creates a pressure that pushes outward, counteracting gravity and allowing the star to remain stable for billions of years. However, this stability is finite. When the nuclear fuel, the hydrogen, is exhausted, the star begins to cool and gravity inevitably takes over, forcing the star to collapse. The star's ultimate fate is determined entirely by its mass. The Indian physicist Subrahmanyan Chandrasekhar calculated the maximum mass a star can possess and still stabilize as a white dwarf. A white dwarf is an extremely dense object, stable because its electrons repel each other, a process governed by the Pauli exclusion principle of quantum physics. This limit is about 1.5 times the mass of the Sun. If the star's mass exceeds this limit, the electron pressure is not strong enough to stop the collapse, and the star continues to shrink dramatically. It may briefly stabilize as a neutron star, another incredibly dense object where gravity has compressed the electrons and protons into neutrons, held up by the neutron's own repulsive force. A neutron star, though only about 10 miles across, is almost as heavy as the Sun. But if the star's mass is even greater than the limit for a neutron star, nothing can stop the collapse. The star shrinks relentlessly, its density increasing until it reaches a point of infinite density and zero size. This is the formation of a singularity and the birth of a black hole. The star's immense gravity warps the surrounding spacetime so severely that light itself cannot escape, forming the event horizon. Everything, matter, light, and information, is trapped forever, leading to the singularity at the center. This profound consequence of general relativity, the creation of an inescapable single point, is the inevitable endpoint for all massive stars. The black hole is the universe's ultimate gravitational prison. The ultimate philosophical ambition of physics is to arrive at the grand synthesis, a single, unified theory that reconciles all four fundamental forces and all known physical phenomena. We have seen the partial success of unifying the strong-weak and the electromagnetic forces, but the crucial missing piece remains the quantum theory of gravity. The clash between general relativity, smooth large-scale, and quantum mechanics, discrete small-scale, is the greatest obstacle. General relativity predicts infinities at the singularity, a mathematical absurdity that shows both theories are incomplete. The search for the final theory led physicists to increasingly abstract concepts. Supergravity theory. Proposed in the 1970s, this theory introduced the concept of supersymmetry, suggesting that every force-carrying particle must have a corresponding matter particle. This was an attempt to make the infinities cancel each other out through the pairing of positive and negative infinities. However, the mathematical calculations were too complex to prove its consistency. String theory. Gained prominence in 1984, this theory proposed a radical shift. Elementary particles are not zero-dimensional points, but tiny, one-dimensional strings. The different vibrations of these strings correspond to the different types of particles and forces, including gravity. String theory successfully provides a quantum description of gravity that avoids the infinities. The major complication of string theory is that it is mathematically consistent only if space-time possesses 10 or 26 dimensions, far more than the 4, 3 space 1 time we observe. The theory suggests that the extra dimensions are compactified, curled up so tightly that they are too small to be observed. Further conceptual refinements led to the realization that different versions of string theory might simply be different approximations of a single, deeper, more fundamental theory, often called M-theory. The possibility of finding the ultimate theory raises questions about its complexity. If a complete theory is found, it will mean that we have discovered the complete set of rules that governs the universe, requiring no arbitrary parameters. The final victory will be in achieving a complete conceptual understanding of why the universe exists and why we are here to observe it. This knowledge should be shared with every ordinary person, not just scientists. The success in establishing the electroweak theory, which proved that the electromagnetic and weak nuclear forces are merely different aspects of a single, unified force at high energies, fueled the ambition to incorporate the strong nuclear force into this framework. This effort is known as the Search for the Grand Unified Theory, or GUT. The basic idea of the GUT is profound. At an incredibly high energy level, far beyond anything achievable in current particle accelerators, the strong nuclear force, the weak nuclear force, and their electromagnetic force all become indistinguishable from one another. They merge into a single unified force. The forces we observe today are simply different aspects of this single, underlying force that separated as the universe cooled. The energy required for this grand unification is estimated to be enormous, far exceeding the energy levels current accelerators can reach. Building an accelerator capable of reaching this unification energy would require it to be the size of the entire solar system, a task currently impossible. However, a scientific theory can be tested not only by replicating the conditions of its formation, but also by observing its consequences in the current universe. The Grand Unified Theory makes an extremely peculiar prediction about the stability of matter itself. It suggests that protons can decay. The proton, the basic unit of normal matter, which we traditionally consider to be stable, should, according to GUT, spontaneously decay into lighter particles such as an anti-electron and other particles. This decay occurs because at the high energies necessary for unification, the fundamental particles inside the proton can sometimes briefly interact via the unified force and break down. The predicted lifetime for a proton is astronomically long, a time span vastly longer than the age of the universe. To test this prediction, scientists cannot simply wait. They must observe a vast number of protons simultaneously in the hope of catching a rare decay event. Experiments, such as one conducted in a salt mine in Ohio, using 8,000 tons of water, have diligently searched for this phenomenon. So far, however, no proton decay has been definitively detected. This negative result means that if proton decay does happen, the proton's lifetime must be even longer than initially predicted, forcing physicists to consider more complex GUT models. Beyond the proton decay test, the GUT is crucial to understanding the universe's most enduring enigma, the matter-antimatter asymmetry. According to the rules of quantum mechanics, the Big Bang should have created equal amounts of matter and antimatter. If this were true, they would have completely annihilated each other, leaving the universe filled only with energy, light, with no galaxies, stars, or planets. Yet we see a universe composed almost entirely of matter. The profound question is, where did the antimatter go? The answer lies in the subtle symmetries of nature. In the 1950s and 60s, a series of shocking discoveries revealed that the weak nuclear force does not respect certain symmetries. It was shown that the weak force breaks p symmetry, mirror symmetry, and CP symmetry, particle-antiparticle symmetry. This means the weak force does not treat a particle and its antiparticle the same way. This asymmetry is vital. It suggests that the antimatter universe would behave differently than our matter universe. If the GUT models can successfully incorporate this CEP violation, they could explain how in the intensely hot, early moments after the Big Bang, a slight preference for matter over antimatter developed, leading to the matter that formed everything we see today. The breaking of CP symmetry also implies the breaking of T symmetry, time reversal symmetry, proving that time flows in an irreversible direction. The success of unifying the strong, weak, and electromagnetic forces, even if incomplete, highlights the central and singular remaining task for modern physics, the incorporation of gravity. The search for a quantum theory of gravity is the key to unlocking the universe's most fundamental mysteries, as it is the only way to reconcile the smooth space-time of general relativity with the probabilistic, quantized reality of the microscopic world. The clash between these two great pillars of 20th century physics is most acutely felt at the singularities of black holes and the Big Bang. Classical general relativity is incomplete because it predicts infinities at these points, telling us nothing about how the universe actually began or what happens inside the event horizon. The problem is that applying quantum principles to gravity leads to uncontrollable infinities. The perpetual creation and annihilation of virtual particles in the quantum vacuum result in infinite energy. According to general relativity, this infinite energy would create an infinite mass, which would warp space-time into an infinite curvature. Since we observe space to be finite and relatively smooth, this contradiction shows that both theories are incompatible at the most extreme levels. The path toward resolving this conflict led physicists to increasingly abstract concepts. One of the first major attempts was supergravity theory in the 1970s. This theory introduced the concept of supersymmetry, suggesting that every force-carrying particle must have a corresponding matter particle. This was an attempt to make the infinities cancel each other out. However, the mathematical calculations required to verify supergravity were so complex that no one was able to complete the proof and confirm its consistency. The next major attempt was string theory, which gained prominence in 1984. String theory proposes a radical shift. Elementary particles are not zero-dimensional points, but tiny one-dimensional strings. The different vibrations of these strings correspond to the different types of particles and forces we observe, including gravity. String theory successfully provides a quantum description of gravity that avoids the infinities because the interaction between two strings is spread out over a finite area, smoothing the quantum fluctuations. The major complication of string theory is that it is mathematically consistent only if space-time possesses 10 or 26 dimensions, far more than the 4, 3 space 1 time we observe. The solution proposed is that the extra dimensions are compactified, curled up so tightly that they are too small to be observed. Further conceptual refinements in the 1990s led to the realization that different versions of string theory might simply be different approximations of a single, deeper, more fundamental theory, often called Abstrum theory. Ultimately, the goal is singular: to find a theory so complete that it requires no arbitrary input, a theory that explains not only how the universe operates but also why its laws and initial state are what they are. This final victory of human reason would be the key to answering the deepest questions of existence. The most immediate and striking consequence of string theory is the existence of extra dimensions. We are intuitively confined to perceiving 3 dimensions of space: up, down, forward, backward, and 1 of time. The idea that there are 6 or 7 additional spatial dimensions, as required by the mathematics of the theory, forces a radical revision of our understanding of space itself. If these extra dimensions are real, the fundamental question is, why are they hidden? The answer lies in the process called compactification. String theory suggests that while the 3 dimensions we experience are vast and extended, the additional dimensions are curled up or compactified into spaces of unimaginably small size at every point in our familiar space. Imagine looking at a simple garden hose from a great distance. It appears to be a one-dimensional line. However, if an ant were walking on it, the ant would experience a second dimension, the circumference of the hose. This circumference is the compactified dimension. For us, observing from afar, this dimension is invisible. Similarly, the extra dimensions are thought to be curled up into incredibly intricate six-dimensional shapes at every single point in our familiar three-dimensional space. The size of these curled-up dimensions is estimated to be near the Planck length, the smallest possible unit of space, which makes them undetectable by our current technology. The profound significance of these hidden dimensions is that they are not mere mathematical curiosities. They are the architects of our physical laws. In string theory, the way the fundamental strings vibrate is entirely dictated by the geometry and shape of the space they inhabit. This means that the precise shape of these hidden extra dimensions determines the physical constants and forces that we observe in our familiar four dimensions. For example, the mass of an electron, the electric charge, the strength of gravity, and even the number of fundamental particle types. All these physical properties are thought to be geometric consequences of the intricate, curled-up structure. This realization transforms the search for the theory of everything into a search for the correct geometry. The final theory will be complete only when the specific, unique geometrical shape of the extra dimensions is identified, as this shape acts as the universe's internal blueprint, dictating every aspect of physical reality. The universe's architecture is far richer and more complex than we ever imagined. Part 32. The Cosmic Landscape and the Multiverse. The complexity introduced by the required geometry of the extra dimensions in string theory leads directly to the contemplation of the multiverse, the idea that our universe is but one among an infinite sea of parallel realities. As we discussed, the physical laws we observe are determined by the specific shape of the extra curled-up dimensions. Unfortunately, the equations of string theory currently allow for an enormous, perhaps infinite, number of possible shapes for these extra dimensions. Each possible shape corresponds to a different stable state, or a different possible universe, each with its own unique laws of physics. This vast collection of possible solutions is called the cosmic landscape. Each stable minimum in this landscape represents a distinct vacuum state where the laws of nature, such as the number of forces, the mass of the Higgs particle, and the value of the cosmological constant, are different. If this landscape is real, and if the universe began with a random quantum process that settled into one of these stable states, then it is plausible that our universe is just one realization within this infinite array of possibilities. The multiverse idea provides a statistical, though controversial, new perspective on the problem of fine-tuning, the observation that our universe's constants are perfectly set to allow for life. Instead of demanding a single highly improbable reason why our universe is perfectly balanced, the multiverse suggests a statistical explanation. If there are an infinite number of universes, every possible set of physical laws is realized somewhere. We simply live in one of the universes where the forces happen to be suitable for the formation of stars, carbon, and intelligent life, because we could not possibly exist in a universe where the laws were chaotic or unsuitable. This view, rooted in the anthropic principle, avoids seeking a miraculous explanation for our existence by suggesting that the observer's presence dictates the environment they perceive. However, the multiverse concept faces severe philosophical and scientific hurdles. The primary difficulty is that these parallel universes, defined by different physical laws, are likely inaccessible to us. If we can never observe or interact with them, the multiverse remains a metaphysical hypothesis rather than a testable scientific theory. The core mission of physics remains finding a single unique theory that explains why our universe, with our specific laws, was realized from this vast infinite array. The contemplation of string theory and its complex, multi-dimensional reality leads to one of the most counterintuitive and profound concepts in modern physics, the holographic principle. This principle suggests that the three-dimensional reality we perceive, the space, objects, and events we interact with, might be merely a hologram, encoded on a distant two-dimensional boundary or surface. This idea originated from the study of black holes. Recall that the entropy, or disorder, of a black hole is proportional not to its internal volume but to the area of its event horizon. This was a shocking discovery, as the entropy of any ordinary physical system is usually related to the number of particles contained within its volume. The fact that a black hole's information capacity is tied to its surface area suggested that the information about the three-dimensional matter that fell in is somehow stored on the two-dimensional boundary. The holographic principle proposes that the fundamental degrees of freedom, the bits of information that define reality, reside not in the three dimensions of space we experience, but on a lower dimensional boundary. Our three-dimensional universe, with its apparent depth and volume, is mathematically equivalent to a two-dimensional system defined on a distant screen. Imagine a security strip on a credit card. When illuminated by light, the two-dimensional strip projects a three-dimensional image. The holographic principle suggests that similarly, the entire three-dimensional reality of the cosmos is mathematically projected from information encoded on a two-dimensional boundary. This concept is supported by a precise mathematical relationship called the AADS/CFT correspondence, which links a specific type of gravitational theory operating in a five-dimensional space to a quantum field theory operating on its four-dimensional boundary. While this correspondence is a highly technical mathematical tool, its philosophical implication is revolutionary. It suggests that gravity and spacetime itself might be emergent phenomena arising from the interactions of particles in a simpler, lower-dimensional quantum system. If the holographic principle is true, it means that the space we inhabit is not fundamentally three-dimensional, but only appears to be so. Our perception of volume and depth is, at the deepest level, an illusion created by the vast amount of information compressed onto a boundary. This idea fundamentally challenges our intuitive connection to space, suggesting that the very texture of reality is simpler and less volumetric than we imagine. The initial formulation of string theory in the 1980s posited that all fundamental constituents of the universe were one-dimensional, tiny vibrating strings. However, as the theory matured in the 1990s, a deeper structure emerged, leading to the development of M-theory. M-theory, short for magic in mystery or membrane theory, is a single overarching theoretical framework that unifies the five consistent versions of string theory. It suggests that strings are not the ultimate elementary units, but are merely one type of object in a richer, 11-dimensional landscape. The new fundamental objects in M-theory are higher dimensional entities called branes, short for membranes. A brane is simply a unit that can have any number of dimensions. A zero brane is a point-like particle. A one brane is the familiar string. A two brane is a sheet or surface. Three branes are three-dimensional volumes. M-theory proposes that our entire three-dimensional universe, including all the matter and forces we perceive, except for gravity, might be confined to the surface of a three-brane that exists within the larger 11-dimensional space. Imagine our universe as a piece of paper, a two-brane floating within a three-dimensional room. Everything on the paper, the cities, the mountains, and the people, is constrained to move only on that two-dimensional surface. In this analogy, the third dimension of the room is the extra dimension that we cannot access. The idea that we live on a three-brane provides a simple, compelling solution to one of physics' great mysteries: the weakness of gravity. Gravity is immensely weaker than the electromagnetic force and the nuclear forces. M-theory suggests that the gravitons, the particles that carry the gravitational force, are not confined to the three-brane on which our matter lives. Instead, gravitons can leak into the extra dimensions of the larger 11-dimensional space. Because the gravitational force is spread out across these extra dimensions, it appears to us on the brane as incredibly weak compared to the other forces, which are confined and therefore strong. M-theory therefore not only unifies the partial theories of physics, but also offers a stunning explanation for the observed weakness of gravity, painting a picture of reality where our entire cosmos is just a membrane floating in a massive, unseen, 11-dimensional bulk. The philosophical goal of the theory of everything is not just to describe matter, but to explain the origin and strength of the fundamental forces that govern the cosmos: gravity, electromagnetism, and the strong and weak nuclear forces. String theory provides an elegant, unified explanation by suggesting that all forces are simply geometric consequences of the multi-dimensional structure of spacetime. Recall that string theory requires 10 or 26 dimensions for its mathematical consistency. The way these extra dimensions are compactified, curled up into tiny, intricate shapes, is what determines the physical laws we observe in our familiar four dimensions. The key insight is that forces and particles are related to vibrations in these dimensions. The graviton, the particle that transmits gravity, is simply one specific vibration pattern of the string. But what about the other forces? The other forces, such as electromagnetism, are mathematically linked to the shape and structure of the extra curled-up dimensions. If the extra dimensions were to somehow expand or change their shape, the strength of the electromagnetic force or the mass of the electron would also change. The forces are not arbitrary. They are the geometric echoes of the hidden architecture of space. Imagine the extra dimensions as a complex, microscopic structure attached to every point in our visible space. The interactions we perceive as forces are really just the ways in which particles, represented by vibrating strings, move through or interact with the intricate geometry of this hidden structure. This unification is far more profound than the previous, separate descriptions of forces. It suggests that all of physics, once divided into separate fields like gravity, particle physics, and electromagnetism, is rooted in a single common origin: geometry. The physical universe is a universe of geometric possibilities. The implications for the search for the theory of everything are immense. If the theory is found, it will not be enough to write down the equations of the vibrating strings. The theory will be complete only when the precise geometric structure of the curled-up dimensions, the exact intricate shape that dictates all the constants, is identified. This realization fundamentally changes the nature of the inquiry. The search for a unified theory becomes a search for the right geometry, the specific architecture of the universe that results in the physical laws we measure in our laboratories and observe in the cosmos. The complexity of this geometrical problem, with potentially billions of possible shapes, underscores the monumental challenge that remains in completing the final theory. We must now consider the consequences of uniting general relativity and quantum mechanics at the smallest imaginable scales. We established that the failure to merge these theories lies in the infinity problem, where the calculated energy of the quantum vacuum causes space-time to collapse mathematically. But what does quantum mechanics suggest about space-time itself at these extreme sizes? As we approach the scale known as the Planck length, an unimaginably small distance that defines the size where quantum effects dominate gravity, the smooth, gentle geometry of space-time as described by Einstein must necessarily break down. At this minute scale, the uncertainty principle takes over. Just as the position and velocity of a particle become fundamentally uncertain, so too must the geometry and topology of space-time itself become uncertain. Space-time is no longer a smooth, predictable fabric. Instead, it becomes a chaotic, constantly fluctuating mess known as quantum foam. Imagine looking at the surface of a pond. From a distance, it appears flat and smooth. As you zoom in closer, you see small ripples. Zoom in further still, and you see the chaotic bubbling and surging of individual water molecules. Similarly, as we zoom into the fabric of space-time at the Planck scale, the fabric itself is not flat. It is boiling with extreme curvature and energy fluctuations. This quantum foam is a consequence of the intense momentary violations of energy conservation allowed by the uncertainty principle. Tiny amounts of energy can spontaneously appear and disappear, causing the geometry of space to fluctuate wildly. Miniature wormholes, tunnels connecting disparate parts of space might flicker into and out of existence, and the topology of space, its fundamental shape, is constantly changing. In this region of quantum foam, the classical concepts of distance and time lose their definite meaning. The very structure of space-time is fuzzy and probabilistic. String theory offers a conceptual way to navigate this quantum foam. Recall that the fundamental strings are themselves incredibly tiny. Their size is approximately the Planck length. Because the strings are the fundamental building blocks, they cannot probe distances smaller than their own size. The strings effectively smooth out the raging turbulence of the quantum foam. According to string theory, the chaotic geometry below the Planck length is replaced by the orderly, if multidimensional geometry of vibrating strings. The idea of quantum foam forces us to realize that our perception of the universe's continuity is an illusion born of scale. Reality, when examined at its absolute foundation, is a shimmering, probabilistic, and radically uncertain environment where the very nature of existence is momentarily being renegotiated at every point. We return to the most persistent philosophical puzzle posed by physics, the apparent flow of time. Our internal experience tells us that the present moment is constantly advancing, that time is moving, and that the future is constantly being born out of the past. Yet the foundational theories of the cosmos, relativity and quantum mechanics, strongly suggest this intuitive flow is an illusion. In the block universe view, which arises naturally from Einstein's special relativity, all moments in time, past, present and future, are equally real and fixed, simply existing as points in the four-dimensional spacetime continuum. There is no special universal present moment. If there is no universal now, then there is no objective cosmic mechanism driving us from one moment to the next. The feeling of temporal flow that time is going by is believed to be a purely psychological phenomenon arising from how our consciousness processes information and forms memories. Our minds perpetually update their perception of reality, creating the illusion of moving through the dimension of time. This internal experience is intrinsically linked to the thermodynamic arrow of time, the cosmic tendency toward increasing disorder. Because memory formation is an irreversible process tied to increasing entropy, our consciousness is hardwired to record events in a sequence, creating a memory of a lower entropy past and anticipating a higher entropy future. This asymmetry in our recording process is what gives time its apparent direction and flow. If we could somehow stand outside of the block universe and view all of space-time in its entirety, we would see a static fixed tapestry of events. The Big Bang and the Big Crunch, or the ultimate freezing of the universe, would all simply exist. The human lives within this block would be fixed, defined trajectories. The mystery of time's flow, therefore, transitions from a problem of external physics to a problem of internal consciousness. The physics provides the static four-dimensional stage, but the biological process of memory and perception creates the dramatic sensation of moving through it. This realization forces us to confront the deep challenge of understanding how the ordered, physical structure of the brain gives rise to the elusive, flowing nature of subjective experience. To understand the core conflict between gravity and quantum mechanics, we must gain a deeper appreciation for the nature of reality at the subatomic level, specifically the concept of quantum fields. Modern quantum mechanics views the universe not as being composed of discrete billiard ball particles, but as being filled with pervasive universal fields. Every type of particle we know, electrons, quarks, and even photons, is merely an excitation or a vibration in its corresponding quantum field. The electron is an excitation of the electron field, the photon is an excitation of the electromagnetic field, and so on. These fields fill all of space and time. This view of reality is crucial to understanding the behavior of virtual particles. The uncertainty principle dictates that in the short term, energy conservation can be temporarily violated. This allows energy to spontaneously materialize as a particle-antiparticle pair and then instantly vanish or annihilate, returning the energy to the field. These fleeting self-annihilating disturbances are called virtual particles. The process occurs continuously and everywhere. The vacuum of space is not truly empty. It is a roiling sea of these temporary particles constantly popping into and out of existence. They are virtual because they cannot be directly detected, but their effects are measurable. One measurable effect is the Casimir effect. If two uncharged parallel metal plates are placed extremely close together in a vacuum, the pressure of the virtual particles pushing on the plates from the outside is slightly greater than the pressure of the virtual particles pushing on the plates from the inside. This is because only virtual particles with wavelengths small enough to fit between the plates can exist inside. This pressure difference causes the plates to be pushed together by a small measurable force, providing concrete evidence that the quantum vacuum is a real active medium. However, the reality of virtual particles is precisely what leads to the infinity problem in quantum gravity. Although fleeting, these virtual particles represent an enormous amount of energy in the quantum vacuum. When physicists calculate the total energy density of all these virtual fields combined and apply it to general relativity, the answer is catastrophically infinite. The universe's actual measured energy density, which accounts for the expansion we observe, is far, far smaller than the theoretically calculated value of the virtual particle energy. This massive, inexplicable discrepancy between quantum theory and gravity is known as the cosmological constant problem and remains the single greatest failure of modern physics, demanding a complete, unified theory for its resolution. The contemplation of string theory and its complex multi-dimensional reality leads to one of the most counterintuitive and profound concepts in modern physics, the holographic principle. This principle suggests that the three-dimensional reality we perceive, the space, the objects and events we interact with, might be merely a hologram encoded on a distant two-dimensional boundary or surface. This idea originated from the study of black holes. Recall that the entropy, or disorder, of a black hole is proportional not to its internal volume but to the area of its event horizon. This was a shocking discovery, as the entropy of any ordinary physical system is usually related to the number of particles contained within its volume. The fact that a black hole's information capacity is tied to its surface area suggested that the information about the three-dimensional matter that fell in is somehow stored on the two-dimensional boundary. The holographic principle proposes that the fundamental degrees of freedom, the bits of information that define reality, reside not in the three dimensions of space we experience, but on a lower dimensional boundary. Our three-dimensional universe, with its apparent depth and volume, is mathematically equivalent to a two-dimensional system defined on a distant screen. Imagine a security strip on a credit card. When illuminated by light, the two-dimensional strip projects a three-dimensional image. The holographic principle suggests that similarly, the entire three-dimensional reality of the cosmos is mathematically projected from information encoded on a two-dimensional boundary. This concept is supported by a precise mathematical relationship called the ADS/CFT correspondence, which links a specific type of gravitational theory operating in a five-dimensional space to a quantum field theory operating on its four-dimensional boundary. While this correspondence is a highly technical mathematical tool, its philosophical implication is revolutionary. It suggests that gravity and space-time itself might be emergent phenomena, arising from the interactions of particles in a simpler lower-dimensional quantum system. If the holographic principle is true, it means that the space we inhabit is not fundamentally three-dimensional, but only appears to be so. Our perception of volume and depth is, at the deepest level, an illusion created by the vast amount of information compressed onto a boundary. This idea fundamentally challenges our intuitive connection to space, suggesting that the very texture of reality is simpler and less volumetric than we imagine. The initial formulation of string theory in the 1980s posited that all fundamental constituents of the universe were one-dimensional, tiny vibrating strings. However, as the theory matured in the 1990s, a deeper structure emerged, leading to the development of M-theory. M-theory, short for magic mystery or membrane theory, is a single overarching theoretical framework that unifies the five consistent versions of string theory. It suggests that strings are not the ultimate elementary unit to Saussure, but are merely one type of object in a richer, 11-dimensional landscape. The new fundamental objects in M-theory are higher dimensional entities called branes, short for membranes. A brane is simply a unit that can have any number of dimensions. A zero brane is a point-like particle. A one brane is the familiar string. A two brane is a sheet or surface. Three branes are three-dimensional volumes. M-theory proposes that our entire three-dimensional universe, including all the matter and forces we perceive, except for gravity, might be confined to the surface of a three-brane that exists within the larger 11-dimensional space. Imagine our universe as a piece of paper, a two-brane, floating within a three-dimensional room. Everything on the paper, the cities, the mountains, and the people, is constrained to move only on that two-dimensional surface. In this analogy, the third dimension of the room is the extra dimension that we cannot access. The idea that we live on a three-brane provides a simple, compelling solution to one of physics' great mysteries, the weakness of gravity. Gravity is immensely weaker than the electromagnetic force and the nuclear forces. M-theory suggests that the gravitons, the particles that carry the gravitational force, are not confined to the three-brane on which our matter lives. Instead, gravitons can leak into the extra dimensions of the larger 11-dimensional space. Because the gravitational force is spread out across these extra dimensions, it appears to us on the brane as incredibly weak compared to the other forces, which are confined and therefore strong. M-theory, therefore, not only unifies the partial theories of physics, but also offers a stunning explanation for the observed weakness of gravity, painting a picture of reality where our entire cosmos is just a membrane floating in a massive, unseen 11-dimensional bulk. To understand the core conflict between gravity and quantum mechanics, we must gain a deeper appreciation for the nature of reality at the subatomic level, specifically the concept of quantum fields. Modern quantum mechanics views the universe not as being composed of discrete billiard ball particles, but as being filled with pervasive universal fields. Every type of particle we know, electrons, quarks, and even photons, is merely an excitation or a vibration in its corresponding quantum field. The electron is an excitation of the electron field, the photon is an excitation of the electromagnetic field, and so on, These fields fill all of space and time. This view of reality is crucial to understanding the behavior of virtual particles. The uncertainty principle dictates that in the short term, energy conservation can be temporarily violated. This allows energy to spontaneously materialize as a particle-antiparticle pair and then instantly vanish or annihilate, returning the energy to the field. These fleeting, self-annihilating disturbances are called virtual particles. The process occurs continuously and everywhere. The vacuum of space is not truly empty. It is a roiling sea of these temporary particles constantly popping into and out of existence. They are virtual because they cannot be directly detected, but their effects are measurable. One measurable effect is the Casimir effect. If two uncharged parallel metal plates are placed extremely close together in a vacuum, the pressure of the virtual particles pushing on the plates from the outside is slightly greater than the pressure of the virtual particles pushing on the plates from the inside. This is because only virtual particles with wavelengths small enough to fit between the plates can exist inside. This pressure difference causes the plates to be pushed together by a small measurable force, providing concrete evidence that the quantum vacuum is a real active medium. However, the reality of virtual particles is precisely what leads to the infinity problem in quantum gravity. Although fleeting, these virtual particles represent an enormous amount of energy in the quantum vacuum. When physicists calculate the total energy density of all these virtual fields combined and apply it to general relativity, the answer is catastrophically infinite. The universe's actual measured energy density, which accounts for the expansion we observe, is far, far smaller than the theoretically calculated values of the virtual particle energy. This massive, inexplicable discrepancy between quantum theory and gravity is known as the cosmological constant problem and remains the single greatest failure of modern physics, demanding a complete, unified theory for its resolution. The cosmological constant problem is arguably the most dramatic and embarrassing failure of modern theoretical physics, directly stemming from the conflict between the microscopic world of quantum mechanics and the macroscopic world of general relativity. Recall that Einstein's original cosmological constant was a term he introduced to balance gravity and maintain a static universe. After the discovery of expansion, he withdrew it. However, the discovery of dark energy in the late 1990s, the mysterious repulsive force causing the universe's acceleration, resurrected the cosmological constant, suggesting that the vacuum of space itself possesses a definite repulsive energy density. The current challenge is to predict the magnitude of this vacuum energy using quantum physics. The vacuum energy, as we established, comes from the energy of the constant creation and annihilation of virtual particles in the quantum foam. When physicists calculate the total possible energy contained in the quantum vacuum, they arrive at a number that is staggeringly large, a massive, almost infinite value. This theoretical prediction suggests that the universe should be expanding so incredibly fast that it would have torn itself apart almost instantaneously after the Big Bang, preventing the formation of any galaxies, stars, or life. Yet we observe the universe to be expanding very slowly and smoothly. When astronomers measure the actual density of the dark energy that is causing the acceleration, they find that its value is tiny, a near zero number. The discrepancy between the predicted quantum vacuum energy and the observed dark energy density is extraordinary. It is a mismatch of roughly 120 orders of magnitude. For the universe to exist as we see it, the infinite vacuum energy predicted by quantum theory must be almost perfectly cancelled out by some other unknown force or mechanism, leaving behind only the tiny residual value we measure as dark energy. The philosophical implication is profound. Why does nature require a delicate, near-perfect cancellation between two enormous numbers? Why is the fabric of space-time so exquisitely balanced between the crushing force of virtual energy and whatever unknown mechanism cancels it out? This problem forces physicists to conclude that either the laws of gravity change on the largest scales, or that the structure of quantum mechanics is incomplete. The mystery of this exquisite cancellation is driving the exploration of string theory in the multiverse. The hope is that the final theory will show that the tiny observed value of the cosmological constant is not a statistical accident, but a mathematically necessary consequence of the universe's ultimate structure. The initial formulation of string theory in the 1980s posited that all fundamental constituents of the universe were one-dimensional, tiny, vibrating strings. However, as the theory matured in the 1990s, a deeper, unified structure emerged. leading to the development of M-theory. M-theory, often considered the single overarching theoretical framework that unifies the 5 consistent versions of string theory, suggests that strings are not the ultimate elementary units, but are merely one type of object in a richer 11-dimensional landscape. The new fundamental objects in M-theory are higher dimensional entities called branes, short for membranes. A brane is simply a unit that can have any number of dimensions. A 0 brane is a point-like particle. A 1 brane is the familiar string. A 2 brane is a sheet or surface. 3 branes are 3-dimensional volumes. M-theory proposes a radical world-changing idea. Our entire 3-dimensional universe, including all the matter and forces we perceive, except for gravity, might be confined to the surface of a 3 brane that exists within the larger 11-dimensional space. Imagine our universe as a piece of paper floating within a multi-dimensional room. Everything on the paper, the cities, the mountains, and the people, is constrained to move only on that 2-dimensional surface. The extra dimensions of the room are those we cannot access. The idea that we live on a 3 brane provides a simple, compelling solution to one of physics' great mysteries: the weakness of gravity. Gravity is immensely weaker than the electromagnetic force and the nuclear forces. M-theory suggests that the gravitons, the particles that carry the gravitational force, are not confined to the 3 brane on which our matter lives. Instead, gravitons can leak into the extra dimensions of the larger 11-dimensional space. Because the gravitational force is spread out across these extra dimensions, it appears to us on the brane as incredibly weak compared to the other forces, which are confined and therefore strong. M-theory, therefore, not only unifies the partial theories of physics, but also offers a stunning explanation for the observed weakness of gravity, painting a picture of reality where our entire cosmos is just a membrane floating in a massive, unseen, 11-dimensional bulk. The theoretical elegance of string theory and M-theory is undeniable, but science requires more than elegant mathematics. It demands experimental verification. The biggest challenge facing these theories is finding a way to test the existence of the unseen, curled-up extra dimensions. Since the extra dimensions are believed to be microscopically small, near the Planck length, traditional experiments cannot detect them. However, if these dimensions are slightly larger than the Planck length, perhaps only a fraction of a millimeter wide, they could potentially leave a measurable imprint on physical laws. One place to look for evidence of extra dimensions is in the behavior of gravity at very small scales. Recall that gravity spreads out into the extra dimensions, which is why it appears so weak to us. If the extra dimensions are relatively large, gravity's strength should increase dramatically over very short distances. Experiments designed to measure the gravitational force between 2 small, closely placed masses are searching for this predicted spike in gravity's strength. Current experiments have placed tight limits on how large these extra dimensions could be, pushing the detectable size down to near the microscopic scale. A second, more dynamic way to search for extra dimensions involves particle accelerators, such as the Large Hadron Collider, LHC. The LHC is designed to smash protons together at incredibly high energies, recreating the conditions of the early universe. If extra dimensions exist, when particles collide, some of the energy might be transferred into gravitons, which then escape into these hidden dimensions. According to the laws of energy conservation, this would result in an apparent loss of energy detected by the LHC's sensors. The missing energy would be the signature of the graviton escaping into the extra dimensions. The successful detection of such an event, a sudden disappearance of energy coupled with a spike in gravity's force at short range, would provide undeniable, empirical proof of the existence of extra dimensions. This would move string theory and M-theory from being purely mathematical constructs to being the confirmed fundamental description of reality. The philosophical implication of such a discovery would be profound, confirming that our perceived reality is only a thin slice of a far vaster 11-dimensional cosmos. The search for these tiny hidden dimensions represents the most urgent experimental task in the 21st century. The search for the theory of everything is not complete just by finding the laws of nature. It must also explain why the universe started in the specific state it did. Even with the elegant framework of string theory or M-theory, the equations describe how the universe evolves, but they do not automatically dictate the initial conditions at the moment of the Big Bang. In classical cosmology, the singularity of the Big Bang was a point of failure where all laws broke down, meaning the initial state could have been anything. chaotic, uniform, or determined arbitrarily by an external force. This lack of predictability at the beginning was profoundly unsatisfying to physicists. The inflationary theory provided a partial answer by showing that a wide range of messy initial conditions could, through rapid expansion, be smoothed out into the uniform cosmos we observe. But even inflation required a starting field and was still constrained by the need for some level of initial order. The most radical theoretical attempt to eliminate the problem of initial conditions altogether is the no-boundary proposal developed by Stephen Hawking and Jim Hartle. This idea utilizes the mathematical concept of imaginary time, where time behaves like another dimension of space. In this framework, the universe is modeled as a finite structure with no edge or boundary. It is analogous to the Earth's surface, finite, yet if you travel on it, you never encounter a beginning or an end. The beginning of the universe, rather than being a sharp singular point of infinite density, becomes a smooth regular point, like the North Pole on a sphere. If the universe has no boundary, then the laws of physics alone, specifically the laws of quantum gravity, would completely determine the initial state. There is no need for an external creator to set the clock or choose the starting conditions. The universe's existence and initial state would be a single, self-consistent mathematical truth, completely determined by the internal logic of the final theory. This realization transforms the ultimate goal of physics. The goal is not merely to describe the universe's mechanics, but to understand the logic of its existence. If the universe is self-contained, its initial conditions are not arbitrary. They are the inevitable consequence of the laws that govern the universe's evolution. The ultimate pursuit of the grand unified theory, or the theory of everything, represents humanity's greatest intellectual ambition, the full comprehension of the cosmos. The philosophical implication of finding this single, complete set of rules would be profound, fundamentally changing our perception of our place in reality. The final unified theory would have to successfully address three main challenges: reconciling gravity and quantum mechanics, solving the infinity problem by showing how the smooth fabric of space-time emerges from the chaotic, probabilistic world of the quantum, likely through the geometrical structure of string theory's extra dimensions, explaining the constants, showing that the seemingly arbitrary physical constants, like the mass of the electron or the strength of the forces, are not random, but are mathematically determined by the internal consistency of the unified theory. Explaining the origin, eliminating the need for arbitrary initial conditions by showing, through principles like the no-boundary proposal, that the universe is self-creating and self-sustaining. If this final theory is discovered, it would imply that we have found the single, self-consistent blueprint for all existence. The distinction between the physical laws and the initial state would vanish, as the laws themselves would dictate the beginning. The most famous expression of this quest for complete knowledge comes from Albert Einstein, who dedicated the last part of his life to this search. The quest is not only scientific but deeply philosophical, reaching back to the questions once reserved for religion. Why do we exist? Why is there something rather than nothing? The discovery of the final theory would be the ultimate victory of human reason. It would allow us to read the mind of the cosmos, not in a theological sense, but in the profound understanding of the complete, rational, and elegant set of rules that governs all reality. Even if the full mathematical complexity of the theory remains challenging for the average person, the conceptual answers, the final comprehensive explanation of our existence, must be understood by everyone. The journey continues, driven by the belief that the universe is comprehensible and that the final unified explanation lies within our grasp. Our journey through the fabric of the cosmos concludes with the most challenging mystery of all, the ultimate fate of the universe, which is now dictated by an entity we cannot see and barely understand: dark energy. For decades, cosmological models predicted that the expansion of the universe, initiated by the Big Bang, must be decelerating, slowing down due to the cumulative, attractive force of all the matter within it. The only question was whether gravity was strong enough to eventually halt the expansion and cause a big crunch, or merely slow it down, allowing a perpetual cooling expansion. However, in the late 1990s, observations of distant supernovae, exploding stars whose predictable brightness allowed astronomers to measure cosmic distances, revealed a shocking truth. The universe's expansion is not slowing down, it is accelerating. This acceleration requires a new, repulsive form of energy, that counteracts gravity on the largest possible scales. This energy is what we call dark energy. It behaves precisely like Einstein's cosmological constant, a term representing a uniform intrinsic energy density within the vacuum of space itself. This dark energy is now the dominant component of the universe's total energy budget, making up roughly 70% of all the energy and matter in existence. Normal matter, the atoms and light we see, makes up only about 5%, with the rest being dark matter. The realization that dark energy is accelerating the universe has profound implications for the cosmic future. The universe will expand forever. Dark energy is an energy of the vacuum, meaning as space expands, more vacuum is created, and thus more dark energy is generated. This creates a self-reinforcing process that ensures the expansion will never halt. A cold, empty future. The accelerating expansion means that over vast stretches of time, all galaxies outside of our local cluster will recede from us at speeds exceeding the speed of light. They will appear to fade away as their light is stretched into invisibility by the expansion of space itself. Our local group of galaxies will eventually be isolated in an empty void. The cosmos is destined for a fate of perpetual, cold isolation, eventually becoming a vast, dark and dilute expanse, where all processes, including the formation of new stars, will cease. The mystery remains. Why is the quantum vacuum so perfectly, yet minutely, energized to cause this slow, accelerating doom? The precise values of the fundamental constants of nature, the speed of light, the charge of the electron, the strength of the nuclear forces, and, critically, the tiny value of the dark energy, are astonishingly fine-tuned to allow for the existence of complex structures and ultimately life. If these constants were shifted by even a small amount, the universe would either collapse immediately, fail to form atoms, or be too diluted to form stars. This observation is the essence of the anthropic principle. The principle states that the laws of nature are what they are because if they were different, there would be no intelligent beings around to observe them. The weak anthropic principle suggests this is a statistical inevitability. If the universe is infinitely large, or if it is one part of a vast multiverse, as suggested by the cosmic landscape of string theory, then every possible set of constants is realized somewhere. We simply find ourselves in one of the lucky few regions or universes where life is possible, for the obvious reason that we couldn't exist elsewhere. The strong anthropic principle goes further, suggesting that the universe must have the properties necessary for life to evolve at some stage. This interpretation flirts with theological ideas, implying that consciousness is central to the cosmos. However, the multiverse explanation, stemming from theoretical physics, offers a way to keep the anthropic principle within the realm of science. If string theory allows for an enormous number of stable solutions, each corresponding to a different universe with different laws, then the fine-tuning of our constants is not miraculous. It is merely a selection effect. This is particularly relevant to the cosmological constant problem. The vast theoretical energy of the quantum vacuum must be cancelled out almost perfectly to yield the tiny observed value of dark energy. In a multiverse, most universes would have uncancelled, catastrophic vacuum energy, but a tiny fraction would have the near-perfect cancellation necessary for the stars and galaxies to form. We exist in one of the latter. This view provides a profound philosophical insight. While science strives to find the single, inevitable truth that dictates all the laws, the existence of a cosmic landscape suggests that the fundamental question might shift from why these laws to which location in the infinite landscape do we inhabit. The anthropic principle, guided by the mathematics of a multidimensional cosmos, helps to explain the existence of life without abandoning reason. The profound search for the ultimate theory of everything leads us to confront the very limits of what is physically and philosophically knowable. Even if physicists successfully unify general relativity and quantum mechanics into a single, elegant equation, two major obstacles remain that may perpetually shield the full truth of the cosmos from our direct apprehension. The first obstacle is the holographic principle. Recall, this concept suggests that the three-dimensional reality we experience might be merely a holographic projection emanating from a two-dimensional boundary. If the reality of space and time is fundamentally emergent, that is, if it arises from a simpler underlying lower-dimensional quantum system, then the ultimate, true description of existence is encoded in a form that our three-dimensional minds are not biologically equipped to grasp. Our human experience, honed by evolution to navigate 3 dimensions of space, may intrinsically limit our ability to visualize or intuitively understand the true texture of reality. The final theory might be a mathematical truth that resists all attempts at human visualization. The second and perhaps more daunting obstacle is the problem of measurement inherent in quantum mechanics. The uncertainty principle tells us that the universe is fundamentally probabilistic. At the core of reality, definite outcomes are replaced by probabilities, and the very act of observation influences the system being observed. Even if we have the complete equations of the universe, they will only provide probabilities for possible outcomes, not to certainties. This means that a strictly deterministic description of the future, as dreamed of by Laplace, is impossible. Furthermore, if the multiverse is real, if the cosmic landscape of string theory produces an infinite array of universes with differing laws, then the final theory we find may not explain why our specific universe was chosen. It would only explain how that choice was mathematically possible. The ultimate horizon of human knowledge might not be a physical boundary like the event horizon of a black hole, but a conceptual one. We may find the final unified set of equations, but we may never fully shed the illusion of flowing time, or the illusion of independent spatial dimensions, because these illusions are intrinsic to our survival and our consciousness. The final theory will reveal the necessary truths of existence, but the ultimate choice of which reality we inhabit, or the psychological feeling of being now, may forever remain questions outside the purview of physics. We conclude our exploration of the fabric of the cosmos by contemplating the final destiny of information and consciousness in a universe ruled by increasing entropy and accelerating expansion driven by dark energy. As the universe expands relentlessly, the thermal energy will become increasingly diluted. Stars will eventually burn out, black holes will evaporate through Hawking radiation, and the space between galaxies will become vast and empty. The universe approaches a state of maximum disorder, or heat death. In this cold, dark future, the primary challenge is the fate of information. The laws of quantum physics suggest that information cannot be truly destroyed. If the universe evolves toward a state where all matter is dispersed and all energy is uniform, the ability to process, store, and access information, the very basis of consciousness, becomes extraordinarily difficult. Some highly speculative theories suggest that life, or at least highly complex sentient processing, might persist in this cold, dilute future. Such entities would have to operate with unimaginable efficiency, utilizing the incredibly small amounts of energy available to perform calculations. The universe, in its final throes, could be seen as a kind of ultimate massive computer, slowly processing information until the very last particles are too separated to interact. However, the laws of thermodynamics impose a harsh limit. Every act of computation, every thought, every memory formed, increases entropy. Eventually, the ability to perform any act of computation will be exhausted, leading to the true cessation of all activity and, arguably, the end of all possible consciousness within our cosmic region. Yet there remains the profound possibility posed by the multiverse. If the cosmic landscape is infinite, then perhaps the finality of our universe is not the end of the story. Our universe might eventually tunnel, or transition into another, more ordered state, another valley in the cosmic landscape, initiating a new, potentially infinitely long existence. The fabric of the cosmos, revealed by this intellectual journey, is not a simple static container. It is a dynamic, multi-dimensional, probabilistic entity that dictates the flow of time and the existence of all things. The ultimate triumph of human reason lies not just in finding the final equations, but in accepting that our limited existence is a fleeting yet magnificent ripple in a reality far grander than we can ever fully experience. The greatest challenge to the multiverse idea and the anthropic principle is the lingering hope that the laws of physics are not arbitrary or random, but are in fact geometrically necessary. This view suggests that the final unified theory, likely M theory, will prove that the fundamental constants we observe are not matters of choice, but are dictated by the inherent mathematical consistency of the 11-dimensional reality. Recall that in string theory, the observed physics of our 4 dimensions is determined by the specific shape and geometry of the 6 or 7 extra curled-up dimensions. Each possible shape in the cosmic landscape corresponds to a different set of physical laws. The multiverse interpretation accepts the possibility of billions of shapes and explains our laws through luck. The counter-argument, the position favouring geometrical necessity, is that only one unique, specific shape for the extra dimensions will be stable or mathematically consistent over vast periods of time. All the other possible shapes might be transient, unstable, or simply mathematically inconsistent when all quantum and gravitational effects are accounted for. If this view is correct, then the geometry of the extra dimensions, and thus the fundamental constants like the electron's mass, the strength of the strong force, and the small value of dark energy, would be determined uniquely by the final theory. The laws would be the only possible laws. This search for the single, geometrically necessary structure is the ultimate quest for uniqueness in physics. If successful, it would resolve the fine-tuning problem without resorting to the multiverse. Instead of claiming our universe is rare among many, it would claim that our universe is inevitable and unique. The entire structure of reality, the texture of space-time, the forces, and the matter would be a single logical consequence of one profound, self-consistent equation. This outcome would confirm the deepest philosophical conviction of thinkers from Plato to Einstein, that the universe is governed by an underlying mathematical elegance that leaves no room for randomness or external choice. The universe exists because it is mathematically compelled to exist in exactly this way. The transition of string theory and M-theory from philosophical frameworks to confirmed science depends entirely on finding experimental evidence that links our visible, four-dimensional world to the hidden, multi-dimensional realm. The search focuses on two key theoretical entities, moduli and gravitons. Moduli are subtle, low-energy fields that correspond to the size and shape of the extra curled-up dimensions. According to the theory, the shape of the extra dimensions should have been fixed very early in the universe. If these dimensions are perfectly fixed, the moduli fields should have an extremely high mass, making them unobservable. However, if the extra dimensions are not perfectly fixed, if they retain some freedom to fluctuate slightly, the moduli fields would have a lower mass and could potentially be detected in high-energy particle collisions, such as those at the Large Hadron Collider, LHC. The discovery of a moduli particle would be direct evidence that the fundamental constants of nature, which are dictated by the shape of the extra dimensions, are not truly constants, but are subject to microscopic fluctuations, confirming the deep connection between geometry and physics. The second crucial experimental test involves the graviton, the hypothetical particle that carries the gravitational force. If the brain-world hypothesis is correct, the idea that our universe is a three-brain floating in a larger space, then the graviton should be able to leak into the extra dimensions. This leakage predicts two specific observable signatures: missing energy. When high-energy particles collide at the LHC, the created gravitons would escape into the extra dimensions, resulting in an apparent loss of energy detected by the particle detectors. This missing energy would be the signature of the graviton disappearing into the larger bulk space. Increased gravity at short range. The leakage suggests that gravity's strength should increase dramatically at extremely short distances as the force is no longer diluted by the entire extra-dimensional volume. Delicate experiments designed to measure gravity's strength between two masses separated by less than a millimeter are searching for this predicted spike in force. The successful detection of either a moduli particle or the signature of graviton leakage would revolutionize physics, providing the empirical link between the universe's dynamic quantum structure and its geometric foundation. It would confirm that the four-dimensional reality we experience is merely a surface on a much grander 11-dimensional structure. The contemplation of the multiverse, arising from the vast number of possible solutions in string theory's cosmic landscape, raises a profound question regarding the ultimate fate of reality itself. If there are infinite universes, each occupying a valley of stable, distinct laws, what is the nature of the space separating them, and what is the relationship between their ultimate destinies? The dominant picture suggests that these different universes, each a distinct bubble with its own vacuum energy, constants, and laws, exist in a larger, eternal and expanding void known as the bulk space, or M-theory's 11 dimensions. These bubble universes are perpetually being created through a quantum process called tunneling. Imagine the cosmic landscape as a complex mountain range. Our universe exists in a specific valley, corresponding to our specific set of physical constants. However, quantum mechanics dictates that the energy state of our universe is not perfectly stable. It can tunnel through a quantum barrier to jump into a different, lower energy valley in the landscape. This tunneling process represents a catastrophic event for the universe, fundamentally changing the physical laws. If our universe were to tunnel to a different, lower energy vacuum state, it would initiate a new phase of cosmic expansion and a sudden, violent change in the constants. This new physics would likely be hostile to all existing life and matter. The electrons might change their mass, the electromagnetic force might change its strength, and all existing atoms would dissolve. The destiny of the multiverse, therefore, is one of perpetual quantum change. Universes are constantly being born, and existing universes are constantly being destabilized through tunneling events. The bulk space is eternal, but the universes that populate it are transient, subject to sudden, unpredictable collapses and rebirths. This contrasts sharply with the simple heat death or big crunch scenarios. The ultimate fate of our reality might not be merely cold and empty, but a violent quantum mechanical transition to an entirely different set of physical laws. The multiverse, while offering a statistical explanation for our existence, simultaneously delivers a destiny defined by fundamental instability at the deepest level of reality. We return to the radical philosophical concept of the holographic principle, which suggests a fundamental connection between the information content of space and its area, rather than its volume. This principle deeply intertwines the destiny of information with the physical reality of space-time. The discovery that the maximum entropy, or information capacity, of a region of space is proportional to the area of its boundary, not its volume, implies that the entire three-dimensional reality we experience could be a projection from a two-dimensional surface. This is analogous to a digital image where all the complex visual information is stored on a two-dimensional sensor or screen. If the holographic principle is correct, it means the entire volume of space we perceive is emergent. It arises from a more fundamental description encoded on its surface. This challenges our deepest intuition about what is real. Our perception of depth, volume, and three spatial dimensions would be the result of a vast, complex quantum encoding on the boundary of the cosmos. This concept has profound implications for the information paradox related to black holes. When matter falls into a black hole, the information it carries appears to be lost forever. However, the holographic principle suggests that the information is not truly lost. It is merely encoded and preserved in a scrambled, two-dimensional form on the black hole's event horizon. When the black hole eventually evaporates through Hawking radiation, this information must somehow be carried away by the emitted particles, though in a highly scrambled form. The area of the black hole's event horizon acts as a quantum memory bank, preserving the record of everything that falls in. The realization that information is conserved and that space-time itself may be a holographic projection forces us to conclude that information is not merely contained in the universe. Information is the fundamental substance of the universe. Reality, at its core, is a massive, intricate pattern of information, and the physical manifestations of space, time, and gravity are simply the ways in which this information is displayed and processed. The fabric of the cosmos is, ultimately, an informational fabric. The conceptual breakdown of absolute time begun by Einstein culminates in the profound mathematical distinction between real time and imaginary time, a concept central to the quantum description of the universe. For centuries, our intuitive understanding defined time using real numbers, describing a relentless, linear progression from a definite past to an unfolding future. This is the real time we experience, governed by the relentless increase of entropy, the thermodynamic arrow. However, to address the problem of the Big Bang singularity and the arbitrary initial conditions required by classical physics, Stephen Hawking and Jim Hartle introduced the mathematical construct of imaginary time. In mathematical terms, imaginary time is related to real time by multiplying by the square root of -1, which physicists denote with the letter I. Philosophically, this transformation makes time behave like a fourth dimension of space study. When the universe is modelled in imaginary time, the structure of space-time becomes Euclidean, meaning it looks and acts like space, where movement in any direction is equally possible. There is no distinction between past and future. One can move forward and backward in imaginary time just as one can move north or south in space. This conceptual shift is crucial for the no-boundary proposal. By working in imaginary time, the singularity, the point of infinite density and mathematical failure, is smoothed out and becomes a regular smooth point, much like the North Pole on a sphere. The universe, when described in imaginary time, has no boundary and no singular beginning. It is a self-contained, finite, four-dimensional geometry. The physics that exists in this imaginary time framework is remarkably simple and elegant. The laws of quantum gravity alone dictate the precise initial state of the universe, removing the need for external creation or arbitrary choices. The challenge, however, is transitioning back to real time. Why do we experience this flow of time, and why did the universe choose to evolve in the real-time direction, where entropy increases? The current scientific understanding is that the simple, elegant structure dictated by imaginary time naturally leads to the complex, asymmetric evolution we observe in real time. The laws of physics, in their purest, boundaryless form, inherently give rise to the relentless, unidirectional flow of time that defines our existence. The deepest philosophical paradox stemming from the collapse of stars is the black hole information paradox. General relativity dictates that all information about the matter falling into a black hole is lost at the singularity. Quantum mechanics, however, asserts that information must be preserved. This conflict is amplified by Hawking radiation, which dictates that the black hole eventually evaporates, leaving nowhere for the information to have gone. To resolve this conflict and harmonize the two great theories of physics, theorists introduced the principle of black hole complementarity. This radical proposal suggests that the physics experienced by an observer falling into a black hole and the physics experienced by an observer safely outside are fundamentally complementary and simultaneous, even though they appear contradictory. For the observer outside the black hole, the event horizon acts like a holographic screen. According to the holographic principle, all the information about the falling matter is encoded and preserved in a scrambled form on the two-dimensional surface of the event horizon, never truly crossing it. From their perspective, the information is never lost but is slowly radiated away by Hawking radiation. For the observer falling in, the experience is entirely different. According to general relativity's equivalence principle, as they cross the event horizon, they feel nothing unusual. From their perspective, they pass the horizon, and the information they carry continues its journey toward the singularity, seemingly unhindered by the horizon itself. Black hole complementarity claims that both descriptions are simultaneously true, but the information cannot be accessed by both observers. The laws of nature conspire to ensure that no single observer can ever measure the information both being preserved at the horizon and being destroyed at the singularity. If an observer tries to cross the horizon to retrieve the falling information, they are inevitably destroyed by the extreme energies near the singularity. This principle is a profound philosophical statement. The fundamental rules of reality are dictated by a form of quantum logic that forbids the observation of paradox. The universe protects its self-consistency by preventing any single observer from witnessing a violation of its core laws. The resolution of the information paradox, therefore, is not a simple physical answer, but a redefinition of what a complete observation means in a universe governed by quantum gravity. The deepest challenge to our intuitive understanding of space and time comes not just from gravity, but from the most bizarre phenomenon in quantum mechanics: quantum entanglement. This phenomenon suggests that space, as we perceive it, is not the fundamental reality. Quantum entanglement occurs when two or more particles become linked together in such a way that they share the same fate, regardless of the distance separating them. Imagine creating two photons whose properties, such as their polarization or spin, are correlated. Even if you send one photon to the Andromeda Galaxy and keep the other on Earth, the moment you measure the property of the photon on Earth, you instantaneously know the corresponding property of the distant photon. This instantaneous link seems to directly violate Albert Einstein's special theory of relativity, which dictates that nothing can travel faster than the speed of light. Einstein famously referred to this phenomenon as spooky action at a distance, arguing that it proved quantum mechanics must be incomplete because it violated the principle of locality, the idea that an event at one point in space can only influence a nearby point after a delay bounded by the speed of light. However, experiments have repeatedly confirmed that this spooky correlation is real, even when the particles are separated by vast distances. The resolution to the apparent paradox lies in recognizing what is not being transmitted faster than light. While the correlation is instantaneous, no information that is useful for communication, like sending a message, can be transmitted faster than light. This is because the outcome of the initial measurement, the one on Earth, is fundamentally random according to the rules of quantum mechanics. You cannot pre-select the outcome, you only know that the distant particle will match the random outcome you measured. Therefore, the speed limit of the cosmos remains intact. The philosophical implication of entanglement is profound. It suggests that the space separating the two particles is, in some fundamental way, irrelevant. The particles behave as a single, unified quantum system despite the spatial separation. This leads to the radical idea that space itself might be an emergent phenomenon. Perhaps the underlying reality is a highly connected quantum information network, and the three-dimensional space we experience, the distance between two entangled particles, is merely the result of how our minds process and organize this information. Entanglement suggests that at the deepest level, the universe is not made of separate objects in space. It is a single, interconnected, whole quantum fabric. We return to the architecture of the cosmos, examining how the interplay of mass, energy, and the geometry of space-time dictates the fundamental shape and destiny of the entire universe. The overall geometry of the universe is described by three possibilities, all determined by the universe's average mass-energy density compared to a critical value. Positive curvature, closed universe. If the total density of the universe, including dark matter and dark energy, is greater than the critical density, the geometry of space is spherical, like the surface of a giant sphere. In this model, light rays emitted parallel to each other would eventually converge, and the universe is finite in spatial extent. In classical cosmology, this geometry predicts that gravity would eventually halt the expansion and lead to a big crunch. Negative curvature, open universe. If the total density is less than the critical density, the geometry of space is hyperbolic, like a saddle or trumpet. In this model, light rays would diverge, and the universe is infinite in spatial extent. This geometry predicts that the expansion will continue forever, resulting in eternal cooling, heat death. Zero curvature, flat universe. If the total density is exactly equal to the critical density, the geometry is flat, obeying the familiar rules of Euclidean geometry, where parallel lines never meet. Observations from the cosmic microwave background have overwhelmingly confirmed that the universe is extremely close to this flat geometry. The extreme closeness to flatness is one of the great puzzles solved by the inflationary theory. As discussed earlier, the rapid expansion during inflation naturally drove the universe's geometry toward the critical density, flattening it out. However, this geometrical flatness is not the final word on destiny. The ultimate fate is now governed by dark energy. Even though the geometry is flat, zero curvature, the accelerating expansion driven by the repulsive force of dark energy ensures that the universe will continue to expand forever, overriding the gravitational pull of all matter. Thus, the cosmos is defined by a paradox. Its geometry is flat, which classically suggests a gently slowing expansion, but its dynamics are open, meaning the presence of dark energy guarantees perpetual, accelerating separation. This insight underscores that space-time is not a mere backdrop. Its geometry and its energy content, including the mysterious dark energy, are inseparable, defining the ultimate texture and destiny of reality. We approach the final contemplation, not of the universe's mechanics, but of humanity's role in the vast, indifferent cosmos. Why should we, creatures confined to a tiny fleeting moment on a small planet, dedicate ourselves to deciphering the laws of infinity and eternity? The pursuit of the theory of everything, the grand synthesis of general relativity and quantum mechanics, is driven by a deep, innate human characteristic, curiosity. Since the dawn of civilization, we have refused to accept the universe as a chaotic, unpredictable mystery. We have always sought patterns, rules, and an underlying order that makes existence comprehensible. The search for the final theory is the modern culmination of this ancient quest. It represents the belief that the universe is not only governed by rational laws, but that these laws are discoverable by the human intellect. The success we have achieved, from predicting the existence of black holes to building the framework of string theory, is a testament to the power of human reason. If the final unified theory is discovered, it would imply that we have, in essence, found the complete, self-consistent blueprint for all existence. This knowledge would allow us to answer the deepest philosophical questions with scientific rigor. Why do the constants of nature have their specific values? Why is the universe dominated by matter, not antimatter? Did the universe have a beginning, and what is its ultimate fate? The final theory, according to the no-boundary proposal, might demonstrate that the universe is self-creating and self-sustaining, requiring no external intervention for its existence or its initial state. This would mark the ultimate triumph of reason, providing a rational, complete explanation for reality. The profound responsibility of finding this final theory does not belong solely to scientists. As the nature of space, time and matter is revealed to be far stranger than our common sense allows, the conceptual breakthrough must be shared. The final knowledge, the answer to why we exist, must be understood by every individual. This pursuit of knowledge is not merely a scientific endeavour, it is a defining characteristic of our species. To know the laws of the cosmos is to understand our deepest physical and philosophical connection to the fabric of reality. We conclude our exploration of the fabric of the cosmos. Our journey has led us through a radical redefinition of reality. Space is not empty, but a dynamic, stretchable, physical entity fused with time. Time is not absolute, but is relative, with its flow rate dependent on speed and gravity. Matter is not made of points, but potentially of tiny, vibrating strings and higher dimensional membranes. Reality is not solely four-dimensional, but exists within a larger, hidden geometry of 10 or 11 dimensions. Our universe may be just one bubble within a multiverse landscape of infinite possibilities. The ultimate texture of reality is revealed to be one of geometric complexity and quantum uncertainty. The central conflict between the continuous, smooth geometry of general relativity and the discrete, probabilistic nature of quantum mechanics remains the key to the unknown. The quest for M-theory and the experimental search for extra dimensions represent the unfinished symphony of physics. If we find evidence for the leakage of gravitons or the existence of moduli particles, the puzzle will begin to snap into place. Ultimately, the most enduring legacy of this search is the transformation of our philosophical perspective. We recognize that the universe in its entirety is interconnected. The distance between two entangled particles is irrelevant. The flow of our subjective time is tied to the vast thermodynamic fate of the cosmos. Our fundamental existence is a consequence of the geometrical architecture of unseen dimensions. The fabric of the cosmos is far stranger, more mysterious, and more magnificent than we ever imagined. The final answer may lie just beyond our reach, but the persistent search for it illuminates the vast capacity of the human mind to understand the deepest truths of existence.